The timestamp reads precisely 9 hours 18 minutes and 42 seconds Mars local mean solar time, October 2nd, 2025, in the vast expanse of Jezero crater. NASA's Perseverance rover continued its methodical exploration of the Martian surface, its instruments scanning ancient river deltas for signs of microbial life that might have existed billions of years ago. But on this particular morning, as the pale Martian sun climbed through the thin atmosphere, Perseverance's upward-facing Skycam captured something extraordinary. The Skycam isn't designed for astronomical observation. It's a wide-angle monitoring system mounted on the rover's top deck, intended to track atmospheric phenomena, dust devils spiraling across the crater floor, wispy clouds of water ice forming in the thin air, the subtle changes in atmospheric opacity as global dust storms develop and dissipate thousands of kilometers away. It's a weather camera, essentially, designed to help mission planners understand the environmental conditions affecting the rover's operations. But on October 2nd, it captured something else entirely. The image shows the characteristic fisheye distortion of the Skycam's wide-angle lens, with the circular housing of the camera itself visible at the edges of the frame. The Martian sky appears in its typical butterscotch hue, lighter near the horizon where dust particles scatter sunlight, darker overhead where the thin atmosphere provides less interference, and there, in the upper portion of the frame, circled in vivid green by NASA's own image processing team, is an object that shouldn't be there. It's not a dead pixel. Dead pixels don't move between sequential frames. It's not a cosmic ray strike. Cosmic ray artifacts appear as brief streaks or dots and vanish immediately. It's not atmospheric phenomena. Dust devils and clouds move across the surface, not through the high atmosphere where this object appears to be located. It's something else. Something moving deliberately through the Martian sky at an altitude and trajectory that suggests it's not of Martian origin. The object appears again in subsequent frames, having moved relative to the background stars. The movement is subtle but measurable, indicating actual motion through space rather than instrumental artifacts. Whatever Perseverance's Skycam captured, it was real, it was there, and it was approaching Mars. NASA published these images in their raw data archive within hours of receiving them from Mars. This wasn't unusual. The space agency maintains a policy of rapid data release for most Perseverance observations. The images flow through an automated pipeline, captured by the rover, transmitted to orbiting spacecraft serving as communication relays, beamed across interplanetary space to NASA's Deep Space Network stations on Earth, processed at the Jet Propulsion Laboratory in Pasadena, and uploaded to public servers where anyone with an internet connection can browse through them. The process typically takes between 6 and 48 hours, depending on communication windows and data priorities. For the October 2nd Skycam images, the turnaround was remarkably fast, less than 12 hours from capture to public availability. Someone at NASA noticed the object quickly enough to add the green annotation, highlighting it in the frame. The annotation appeared on NASA's official multimedia pages, not buried in technical archives but prominently featured where journalists and space enthusiasts would inevitably find it, and find it they did. Within days, the image was circulating across social media platforms, astronomy forums, and news websites. The object was identified as 3I Atlas, an interstellar comet that had been discovered just months earlier and was now making its closest approach to Mars. Here was visual confirmation, captured by humanity's most advanced Mars rover, showing a visitor from another star system in the Martian sky. But here's what makes this moment truly significant. October 2nd was not the day of closest approach. That was scheduled for October 3rd, 24 hours later, when 3I Atlas would pass within 29 million kilometers of Mars, the closest any human-made instrument had ever been to an interstellar object. On October 2nd, the comet was still incoming, still brightening, still revealing more detail as it approached its nearest point to the red planet. So the question that would soon consume the astronomical community was simple. If Perseverance captured this on October 2nd, what did it capture on October 3rd? The answer as it turned out, would be the beginning of one of the most carefully orchestrated silences in the history of space exploration. To understand why October 3, 2025 represents such an unprecedented opportunity and why the subsequent silence is so meaningful, we need to examine the extraordinary celestial mechanics that brought 7 spacecraft into perfect position to observe 3I Atlas during its Mars flyby. The geometry was nothing short of remarkable. At 4 o'clock Coordinated Universal Time on October 3rd, 3I Atlas reached its closest approach to Mars at a distance of 29.7 million kilometers. In astronomical terms, this represented an almost impossibly intimate encounter with an interstellar visitor. For comparison, when Oumuamua, the first confirmed interstellar object, was discovered in 2017, it was already moving away from us at tremendous speed, visible only as a rapidly fading point of light. When Borisov was found in 2019, we had better advance warning. But even our most powerful telescopes could resolve it as little more than a fuzzy blob. With a faint tail, 3I Atlas was different. Discovered in July 2025 by the Atlas Asteroid Survey Network. While still 4 for astronomical units from the Sun, it provided months of advance warning. More importantly, its trajectory was taking it through the inner solar system in a way that would bring it tantalizingly close to multiple worlds: Mars in October, Jupiter in March 2026. For the first time in human history, we had the opportunity to observe an interstellar visitor not as a distant, departing speck, but as a detailed, approaching object that we could study with multiple spacecraft from multiple vantage points. The spacecraft constellation that awaited 3I Atlas at Mars was unprecedented in both number and capability. Let's examine each one and understand what it brought to this moment. NASA's Mars Reconnaissance Orbiter MRO had been circling Mars since 2006, making it one of the longest-serving active spacecraft at the Red Planet. Its crown jewel was the HiRISE camera, the high-resolution imaging science experiment capable of resolving surface features down to 30 centimeters from its typical orbit altitude of 300 kilometers above Mars. But on October 3rd, HiRISE was pointed not at the Martian surface, but outward into space, toward a target 29 million kilometers away. From that distance, HiRISE's resolution would be approximately 30 kilometers per pixel when imaging 3I Atlas. This might not sound impressive until you realize that this represented the highest resolution imaging of an interstellar object ever achieved. Every previous interstellar visitor had been observed only as unresolved points of light. Here was the chance to actually see structure, to distinguish the nucleus from the coma, to observe details that could reveal whether this object was behaving like a typical comet or displaying anomalous characteristics. The European Space Agency's Mars Express orbiter, operational since 2003, carried its own suite of instruments capable of contributing unique data to the observation campaign. The high-resolution stereo camera could potentially create 3-dimensional maps of 3I Atlas's coma structure, revealing asymmetries in gas and dust distribution that might indicate non-uniform outgassing or even artificial geometry. The OMEGA spectrometer could analyze the chemical composition of material being released from the object's surface, providing detailed information about its formation environment and current activity. ESA SX, Mars Trace Gas Orbiter, a more recent arrival at Mars, brought even more sophisticated instrumentation to bear on the problem. The NOMAD spectrometer system was designed to detect trace gases in Mars's atmosphere with extraordinary sensitivity. But when pointed at 3I Atlas, it could analyze the spectral signatures of the comet's coma with unprecedented precision. The CASIS camera system could provide high-resolution color imagery, complementing the observations from other spacecraft. NASA's Mars Odyssey orbiter, launched in 2001 and still operational after more than 2 decades, contributed thermal infrared observations through its THEMIS instrument. Any anomalous heat signatures, any unexpected thermal activity, any hot spots that shouldn't exist on a natural comet would be detectable by THEMIS's sensitive infrared sensors. NASA's Perseverance rover represented the only ground-based observer with a direct line of sight to 3I Atlas during closest approach, while its Skycam had already captured the object on October 2nd. The rover carried multiple other instruments capable of contributing to the observation campaign. The SuperCam spectrometer could potentially detect the chemical signatures of the comet's coma. If it became bright enough, the rover's other cameras could track the object's apparent motion and brightness changes over time. China's Tianwen-1 orbiter added an entirely different perspective to the observation constellation. Since arriving at Mars in February 2021, Tianwen-1 had demonstrated impressive imaging capabilities, capturing thousands of high-resolution images of the Martian surface and atmosphere. The China National Space Administration had been remarkably prolific in releasing these images, over 14,000 in the 4 years since arrival, an average of nearly 12 per day. For 3I Atlas, Tianwen-1's instruments were positioned to provide yet another independent view of the interstellar visitor. The United Arab Emirates Hope orbiter Alamol completed the constellation with its unique elliptical orbit that provided extended observation windows. Hope's Emirates Mars infrared spectrometer and other instruments were designed for atmospheric studies, but were equally capable of gathering spectroscopic data on a passing comet. 7 spacecraft. For space agencies, 3 continents, all positioned around Mars with their instruments trained on the same target, during the same narrow window of time. The level of international coordination required to achieve this was extraordinary in itself. Spacecraft operations are planned months in advance, and aligning multiple missions from different agencies requires careful diplomacy and technical coordination. But the coordination didn't stop with the Mars-based assets. Ground-based telescopes around the world were also positioned to observe 3I Atlas during its Mars flyby, though their observations would be limited by the object's low apparent brightness and its position in the sky during daylight hours. For many Earth-based observers, the real action, the unprecedented close-up observations, would come from the spacecraft already stationed around Mars. The timing was perfect. The geometry was optimal. The instrumental capabilities were extraordinary. For a few precious hours on October 3, 2025, humanity possessed the finest view of an interstellar visitor that had ever been achieved, or might ever be achieved again. And then, silence. Not the silence of instruments failing or communications links going down, not the silence of technical difficulties or data processing delays, but the silence of coordination, the silence of consultation, the silence of multiple independent space agencies, simultaneously deciding that whatever they had observed needed careful consideration before being shared with the world. In the days following October 3rd, that silence would become more conspicuous, more deliberate, and more troubling with each passing hour. By October 7, 2025, the silence surrounding 3I Atlas had evolved from curious to concerning to genuinely disturbing. For days had passed since the most detailed observations of an interstellar object in human history, and the world's space agencies had released precisely nothing. To understand how abnormal this was, one needs to appreciate the typical rhythm of space mission data release. Modern space agencies operate under principles of scientific transparency and public engagement that have been refined over decades of experience. When spacecraft capture interesting data, that data typically flows to the public through well-established channels with predictable timing. NASA's approach to Mars mission data is particularly systematic. The Mars Reconnaissance Orbiter regularly releases high-res images within days of acquisition, often accompanied by detailed explanations from planetary scientists. These aren't just routine mapping photographs, they include dramatic observations of dust devils in action, avalanches cascading down crater walls, seasonal changes in polar ice formations, and newly formed impact craters still surrounded by their debris fields. The images appear on NASA's website with explanatory captions, get featured in press releases, and are shared across the agency's social media platforms. The European Space Agency follows similar protocols with Mars Express, when the spacecraft observes something noteworthy unusual atmospheric phenomena, interesting geological formations, seasonal changes in surface features. ESA publishes the data relatively quickly. They write detailed articles explaining the significance of the observations, invite planetary scientists to provide commentary, and ensure that the information reaches both the scientific community and the general public. But perhaps most telling was the silence from China's space program. The China National Space Administration has, if anything, been even more aggressive than NASA or ESA in publicizing their Mars mission achievements. Space exploration represents a matter of national prestige for China, with every successful operation serving as a demonstration of technological capability to the world. When Tianwen-1 entered Mars orbit in February 2021, CNSA released high-resolution images within hours. When the Zhurong rover successfully landed on the Martian surface in May 2021, images from the surface appeared almost immediately color-corrected, professionally processed and widely distributed to international media. The Chinese flag painted on the lander's surface featured prominently. In many of these early releases, a clear statement about China's arrival as a major spacefaring power. Since Tianwen-1's arrival at Mars, CNSA had maintained this pace of publication. Over 14,000 images released in 4 years represents an extraordinary commitment to public outreach and scientific transparency. The images showcase everything from sweeping Martian landscapes to close-up details of rock formations, from the rover's tracks in Martian soil to panoramic views of the landing site. They demonstrate not just scientific capability, but photographic artistry in how they present Mars to Earth-bound audiences. This context makes China's silence regarding 3I Atlas profoundly significant. If Tianwen-1 had captured routine images of the interstellar visitor images showing a typical comet, with a typical coma and tail, CNSA would almost certainly have published them immediately. Such images would have represented a major public relations victory, demonstrating that China's Mars orbiter was capable of capturing data on the most significant astronomical event of the decade. They would have provided evidence of China's advanced imaging capabilities and would likely have been released with considerable fanfare, possibly beating NASA and ESA to the punch in making the first detailed images of 3I Atlas public. But Tianwen-1's data remained unreleased. No images, no press statements, no acknowledgement that observations had even been attempted. This represented a complete break from 4 years of established publication patterns. The silence from the United Arab Emirates was equally notable, though perhaps less surprising given the smaller scale of their space program. The UAE's Hope orbiter had been remarkably transparent with its mission data since arrival at Mars, regularly sharing atmospheric observations and collaborating with international partners on scientific analysis. The Emirates Mars mission had positioned itself as a contributor to global Mars science, not just a national prestige project. Yet for 3I Atlas, Hope remained silent. Meanwhile, the European Space Agency's silence was particularly puzzling given their historical independence from both American and Chinese space programs. ESA routinely operates on its own schedule, releasing data when their scientists determine it's ready for publication. They don't typically wait for NASA's approval or coordinate their announcements with other agencies. ESA's Mars Express and ExoMars Trace Gas Orbiter should have been generating their own independent datasets, ready for publication according to European timelines and European scientific protocols. But ESA, too, remained silent. This wasn't just unusual, it was unprecedented. For independent space agencies operating under different political systems, with different funding structures, different publication policies, and often competitive relationships, to simultaneously maintain silence about the same event suggested coordination at the highest levels. Consider what such coordination would require. Phone calls between agency administrators in Washington, Paris, Beijing, and Abu Dhabi. Discussions about data sharing, analysis timelines, and publication strategies. Agreement on messaging, on timing, on how to present whatever had been observed to the scientific community and the general public. These are not conversations that happen routinely. These are conversations that happen when something unexpected appears in the data, and multiple agencies need time to understand what they're looking at. The silence also extended to the broader scientific community. Typically, when major astronomical observations are conducted, preliminary results begin circulating through informal channels within days. Astronomers talk to colleagues, graduate students present initial findings at seminars, and the outlines of discoveries begin emerging through the scientific grapevine, long before formal publications appear. But not this time. Even the informal scientific communication networks seemed unusually quiet regarding 3I, Atlas. Either the observation teams were maintaining unprecedented operational security, or the data was being held at levels high, enough that working scientists weren't being given access to it. The contrast with the October 2nd Perseverance Skycam image was stark. That image had appeared in NASA's raw data archive, been annotated by NASA's multimedia team, and circulated widely within hours of being captured. It represented exactly what one would expect from routine space mission operations: capture, process, publish, explain. The system had worked as designed, but for October 3rd, the system seemed to have paused. The automatic data pipelines that normally fed observations to public archives appeared to have been interrupted or redirected. The routine processes that typically brought space mission discoveries to public attention had been suspended. As the days passed, this suspension became increasingly conspicuous. Science journalists began asking questions. Amateur astronomers who had been eagerly awaiting the Mars flyby observations started expressing frustration. Online forums dedicated to space exploration filled with speculation about technical difficulties, data processing delays, and government shutdown impacts on NASA operations. The government shutdown explanation had some merit for NASA's silence. As of October 1, 2025, more than 15,000 NASA employees, 83% of the agency's workforce, had been furloughed due to congressional failure to pass appropriations bills. The Jet Propulsion Laboratory, which manages most NASA Mars missions, was operating with skeleton crews. Data processing pipelines that normally operated smoothly were running through bureaucratic complications, but the shutdown only affected the United States. It had no impact on the European Space Agency, the China National Space Administration, or the UAE space program. These organizations operated under completely different funding structures and political systems. They had their own data processing capabilities, their own publication protocols, and their own reasons for maintaining scientific transparency, yet they, too, remained silent. By October 7th, the silence had taken on a weight of its own. In the absence of official information, speculation flourished. Online communities developed elaborate theories about what the spacecraft might have observed. Some suggested technical failures had prevented successful observations. Others proposed that the data was simply taking longer to process than usual. Still others began wondering whether the observations had revealed something so unexpected that multiple space agencies needed time to verify their findings before making any public statements. The silence was becoming the story. Each day without information release made the eventual revelation, whatever it might contain, more significant. If routine cometary observations had been conducted successfully, why the delay? If technical problems had prevented good data collection, why not simply say so? If the observations were successful but showed something unexpected, what could be so surprising that it required international coordination before release? The answers to these questions existed somewhere, in secure facilities at the Jet Propulsion Laboratory in Pasadena, at the European Space Operations Center in Darmstadt, at CNSA headquarters in Beijing, and at the Mohammed bin Rashid Space Center in Dubai. People were looking at data that the rest of the world wasn't being allowed to see. The October 2nd Skycam image remained the only visual evidence available to the public, a single frame showing a small, bright object in the Martian sky, captured one day before the closest approach when 7 spacecraft would have had the best view of an interstellar visitor that humanity had ever achieved. One image from October 2nd nothing from October 3rd. The contrast was becoming impossible to ignore. On October 7, 2025, just as frustration over the continuing silence was reaching a crescendo in astronomical communities worldwide, the European Space Agency finally broke ranks. At 14:30 Central European Time, ESA published a brief announcement on their website, accompanied by a series of images and a short animation showing 3I Atlas moving against the background stars. The release was simultaneously satisfying and frustrating. After 4 days of silence, here was proof that the observations had been successful, that the spacecraft had functioned properly, and that data had been collected. But the images themselves raised as many questions as they answered. The ESA announcement described observations made by the ExoMars Trace Gas Orbiter using its CASIS camera system between October 1st and 7th. The images showed 3I Atlas as what ESA diplomatically termed a slightly fuzzy white dot near the center of the frame. An animation compiled from sequential images demonstrated the comet's motion relative to background stars as it approached and then receded from Mars. Dr. Nicholas Thomas, principal investigator for the CASIS camera, provided technical context that helped explain both the achievement and the limitations of the observations. He noted that 3I Atlas was approximately 10,000 to 100,000 times fainter than CAS-SIS's usual targets. The bright Martian surface features the camera was designed to photograph, capturing the comet at all required 5-second exposures, extraordinarily long for an instrument optimized for planetary surface imaging. The images confirmed several important facts about 3I Atlas. The object possessed a visible coma, the cloud of gas and dust surrounding its nucleus measuring several thousand kilometers across. This was normal cometary behavior, exactly what would be expected as solar radiation heated the object's surface and caused volatile materials to sublime it into space. The coma appeared roughly circular in the images, without obvious asymmetries or unusual structural features. Notably absent from the initial images was any sign of a comet tail. Dr. Thomas explained that while tails form as solar wind pushes gas and dust away from comets, creating the spectacular streamers that can extend millions of kilometers into space, such tails are typically much fainter than the central coma. At the time of observation, if a tail existed, it was too faint for CASIS to detect with its limited exposure capabilities. The technical achievement represented by these observations shouldn't be understated. CASIS was designed to photograph Mars from distances of hundreds to thousands of kilometers, focusing on bright geological features under excellent lighting conditions, successfully imaging a faint interstellar object 30 million kilometers away, roughly 100 times farther than the instrument's typical targets represented. Remarkable flexibility and capability. But the ESA announcement was notable as much for what it didn't say as for what it did reveal. The language was carefully neutral, describing the observations in technical terms without interpretation or analysis. There was no discussion of unusual features, no mention of anomalous behavior, no attempt to place the observations in the broader context of 3I Atlas's puzzling characteristics. More significantly, the announcement revealed that ESA's other Mars orbiter, Mars Express, had also attempted to observe 3I Atlas, but with less success. The older spacecraft's camera was limited to half-second exposures insufficient to clearly capture such a faint target. However, ESA scientists were working to combine multiple Mars Express images through a technique called stacking, adding the signal from several frames to bring out features too faint to see in individual exposures. This raised an obvious question. If ExoMars had successfully captured clear images of 3I Atlas showing normal cometary appearance, why was ESA investing additional effort in extracting more data from Mars Express? The answer suggested they were looking for something specific, something that the initial CASIS observations might not have revealed. The announcement also mentioned that 3 different spectrometers NOMAD on ExoMars, plus Amiga and SPICM on Mars Express had attempted to analyze the chemical composition of 3I Atlas. during the flyby period, but ESA was notably vague about the results of these spectroscopic observations. The statement indicated it was uncertain whether the coma and tail were bright enough. For spectral characterization, this uncertainty was telling. If the spectrometers had failed to detect the comet entirely, ESA would likely have said so directly. If they had obtained good spectra showing normal cometary composition, that would have been worth mentioning as a successful scientific result. The fact that results were described as uncertain suggested that data had been collected, but that its interpretation required additional analysis. The timeline provided by ESA was equally revealing. Scientists would continue analyzing the data over the next weeks and months, not days or even a quick preliminary assessment. This suggested either that the data was more complex than expected, or that whatever had been detected required careful verification before being announced publicly. Dr. Colin Wilson, ESA's project scientist for both Mars Express and ExoMars, made an interesting comment in the announcement. It's always extra exciting to see the orbiters responding to unexpected situations. The word choice was curious. 3I. Atlas had been discovered months in advance. Its flyby trajectory had been calculated precisely. Spacecraft positioning and observation planning had been conducted deliberately, over weeks of preparation. What aspect of this carefully planned observation campaign was unexpected? The ESA release accomplished several things simultaneously. It demonstrated that European spacecraft had successfully observed 3I, Atlas, providing the first official confirmation that the flyby observations had been conducted as planned. It showed images that appeared broadly consistent with normal cometary activity. A fuzzy object with a visible coma, behaving roughly as expected for a comet approaching the Sun. But it also revealed that additional analysis was ongoing, that spectroscopic results were still being evaluated, and that the ESA considered the observations significant enough to warrant extended study. Most importantly, it made the continued silence from NASA, China, and the UAE even more conspicuous if ESA's relatively limited observations were deemed suitable for immediate publication even. With caveats about ongoing analysis, what were the other agencies seeing that required continued secrecy? NASA's Mars Reconnaissance Orbiter carried more powerful cameras than CASA's. Tianwen-1 had demonstrated impressive imaging capabilities over 4 years of Mars operations. These spacecraft should have obtained better images with higher resolution and more detail than the European observations that had just been released, yet their data remained under wraps. The ESA announcement served as a diplomatic pressure valve, demonstrating that 3I, Atlas observations could be shared publicly without causing international incidents or scientific controversies. By releasing their preliminary findings, ESA was essentially saying to their counterparts, here's what we saw, here's what we're comfortable sharing. Now, what about you? The response from other agencies was continued silence. Within hours of the ESA release, science journalists and astronomy enthusiasts were analyzing the European images pixel by pixel, looking for anything unusual or anomalous. The images were subjected to contrast enhancement, brightness adjustments, and comparative analysis with known comets. But CASSIS's resolution limitations meant that detailed structural analysis was impossible. The comet remained a slightly fuzzy white dot, exactly as ESA had described it. The real question was whether higher resolution observations from other spacecraft would reveal details that ESA's images couldn't capture. Were there structural features in the coma that only became visible at better resolution? Were there spectroscopic signatures that only more sensitive instruments could detect? Were there thermal or other anomalies that would only be apparent in data from spacecraft with more sophisticated instrument suites? The answers to these questions existed in the data archives of NASA, CNSA, and the UAE, but 5 days after the closest approach, that data remained locked away, accessible only to the scientists and administrators who had collected it. ESA had provided a tantalizing glimpse of what the October 3rd observations had revealed, but it was only a glimpse, and it left the most important questions unanswered. while space agencies maintained their careful silence about what their instruments had observed. During the October 3rd flyby, the basic orbital mechanics of 3I, Atlas, continued to present one of the most mathematically troubling aspects of the entire situation. The trajectory that brought this interstellar visitor to Mars and that would carry it onward to Jupiter represented a sequence of celestial coincidences so improbable that calling them coincidences began to strain credibility. Dr. Avi Loeb, the Harvard astrophysicist who had gained considerable attention for his analysis of Oumuamua's anomalous properties, had been tracking 3I, Atlas since its discovery and calculating the statistical probabilities of its observed trajectory. His conclusions were uncomfortable for anyone hoping to explain this object through purely natural processes. The first element to consider was the orbital inclination. 3I, Atlas was traveling along a path inclined just for 0.89 degrees relative to the ecliptic plane, the flat disk in which Earth and the other planets orbit the Sun, for an object that formed in another star system billions of years ago, that underwent gravitational ejection from its original home, and then wandered through interstellar space for eons before happening to encounter our solar system. This near-perfect alignment was extraordinary. Consider the three-dimensional geometry involved. Interstellar space is truly three-dimensional. Objects approaching our solar system could arrive from any direction from above the ecliptic plane, from below it, or at any angle in between. The vast majority of possible trajectories would bring a visitor nowhere near the ecliptic disk where the planets reside. Loeb calculated that the probability of an interstellar object randomly arriving with an inclination within 5 degrees of the ecliptic was APPROXIMATELY 0.2% roughly, 2 chances in 1,000. Already quite unlikely, but this was just the beginning of the statistical analysis. The second factor was the timing of planetary encounters. 3I, Atlas wasn't just passing through the ecliptic plane. It was doing so at precisely the right moment to encounter multiple planets. On October 3, 2025, it passed within 29 million kilometers of Mars. On March 16, 2026, it would pass within 54 million kilometers of Jupiter, to close encounters with two of the most scientifically interesting worlds in our solar system after Earth. The probability calculations for this timing were more complex, involving the orbital positions of both planets and the specific trajectory of the interstellar visitor. Mars completes an orbit around the Sun every 687 Earth days, while Jupiter takes nearly 12 Earth years, the window during which both planets would be positioned for close encounters with a single interstellar trajectory was quite narrow. Loeb estimated this probability at approximately 0.02% to 2 chances in 10,000. But the statistical analysis didn't stop there. The distances of closest approach were neither arbitrarily close nor arbitrarily distant. They were, in fact, nearly optimal for spacecraft-based observations. Too close, and an object would zip past before instruments could properly track and observe it. Too far, and the resolution would be inadequate for detailed study. The Mars flyby distance of 29 million kilometers was close enough to provide unprecedented resolution for interstellar object imaging, yet far enough to avoid the gravitational perturbations that might have affected a close encounter. The Jupiter flyby distance of 54 million kilometers was similarly well positioned for extended observation during the object's most active phase after perihelion passage. This optimization of observational geometry added another statistical factor to the analysis. When Loeb combined all elements, the ecliptic alignment, the timing of planetary encounters, and the optimization of approach distances, the combined probability dropped to approximately 0.5%. That's 5 chances in 1 million. 1 in 200,000. To put this in perspective, if you purchased a lottery ticket, you would have better odds of winning a substantial prize than 3I, Atlas had of randomly following this particular trajectory through our solar system. If you shuffled a deck of cards and dealt yourself a specific sequence of 5 particular cards, in exact order, that would be more likely than this orbital configuration occurring by chance. The statistical improbability raised obvious questions about whether the trajectory was, in fact, random. In academic discussions, when probabilities drop below certain thresholds, typically around 0.01% or 1 in 10,000, scientists begin seriously considering whether alternative explanations might be more plausible than random occurrence. One such alternative explanation was the transit survey targeting hypothesis. This elegant theory suggested that 3I Atlas's trajectory wasn't random at all, but had been deliberately calculated to investigate our solar system based on prior detection of its planetary components. Here's how the theory worked. Imagine an advanced civilization located somewhere in our galaxy, perhaps hundreds or thousands of light years away. Like human astronomers, they would be interested in detecting planetary systems around nearby stars. The most successful method developed by human science for finding exoplanets is the transit survey technique, watching stars for tiny decreases in brightness that occur when planets pass in front of them from our perspective. But this method only works if you're positioned correctly relative to the target star system. You need to be located within a narrow cone of space from which the planet's orbital motions would cause them to appear to cross the face of their star. From most locations in the galaxy, our solar system's planets would never transit the Sun as seen from that vantage point, making detection impossible. However, there is a specific region of space, a cone roughly 10 degrees wide, from which virtually all components of our solar system would be detectable via transit surveys. Any civilization located within this cone would be able to detect Earth, Mars, Jupiter, and even the asteroid belt as they periodically crossed the Sun's disk. The mathematics of this detection zone was straightforward to calculate. The asteroid belt, being the thickest component of our solar system's debris disk, would subtend an angle of approximately 10 degrees as seen from a distant vantage point. Any observer located within 5 degrees above or below the ecliptic plane would be positioned to detect asteroid belt transits, and therefore to identify our solar system as containing significant solid material in stable orbits, a clear signature of planetary system formation. If such a civilization decided to send a probe to investigate our solar system more closely, the logical trajectory would be along the same geometric alignment that enabled the original detection. The probe would be launched directly down the pipe of the detection cone, approaching our system along a path inclined at approximately 5 degrees to the ecliptic, exactly the inclination observed for 3I Atlas. This targeting hypothesis explained not just the trajectory, but several other puzzling aspects of 3I Atlas's behavior and timing. A probe designed to survey our solar system would want to encounter multiple worlds during a single pass, maximizing the scientific return on an interstellar journey that might have taken millions of years to complete. The Mars-Jupiter trajectory accomplished exactly this objective. The timing was also suggestive. 3I Atlas would have entered the outer reaches of our solar system approximately 8,000 years ago, when it crossed the heliopause and began to feel the Sun's gravitational and magnetic influence. 8,000 years ago corresponds roughly to the beginning of recorded human civilization, the development of agriculture, the establishment of permanent settlements, the first written records. If an advanced civilization were monitoring our solar system for signs of emerging intelligence, this time period would represent a logical point for increased attention. Not so early that there would be nothing interesting to observe, but not so late that crucial developmental phases would be missed. The statistical analysis provided no definitive proof of artificial origin. 1 in 100,000 events do occur. They're just extremely rare. People win lotteries against enormous odds. Lightning does occasionally strike the same location multiple times. Highly improbable cosmic coincidences do happen in a universe vast enough to contain countless opportunities for unlikely events. But when you are a space agency analyzing data from the most detailed observations of an interstellar object ever conducted, and when that object displays a trajectory with 1 in 100,000 probability while also exhibiting other anomalous characteristics, you begin asking hard questions about what you're actually looking at. Questions about whether the trajectory is trying to communicate something. Questions about whether the timing is deliberate. Questions about whether the object that 7 spacecraft observed on October 3, 2025, was behaving in ways consistent with natural cometary processes or whether it was doing something else entirely. The answers to those questions existed in the data collected during the Mars flyby. High-resolution images that could reveal structural details invisible from Earth-based observations. Spectroscopic data that could confirm or refute the unusual. Chemical signatures detected by ground-based telescopes. Thermal measurements that could detect anomalous heat sources or unusual energy distribution patterns. That data was being analyzed somewhere by teams of scientists with security clearances and non-disclosure agreements in facilities where the implications of highly improbable trajectories could be discussed without public scrutiny. The mathematics didn't lie. The probability calculations were straightforward and verifiable. 3I Atlas was following a trajectory that had less than a 0.0005% chance of occurring randomly. Whether that meant anything significant depended entirely on what those 7 spacecraft had observed when they had their closest look at humanity's most unusual interstellar visitor. Among all the anomalies associated with 3I Atlas, there was one that stood apart from statistical arguments about trajectory and speculative theories about artificial origin. It was a hard, physical observation that challenged fundamental assumptions about how natural objects form and behave. It was the detection of nickel emissions without corresponding ion signatures, a combination that simply doesn't occur in natural cosmic objects. The story began in July 2025, when the Very Large Telescope VLT in Chile's Atacama Desert began systematic spectroscopic observations of the approaching interstellar visitor. The VLT, operated by the European Southern Observatory, represents one of the most sophisticated ground-based astronomical facilities on Earth. Its 8.2-meter unique telescopes can be operated independently or combined through interferometry to achieve the resolution of a much larger instrument. Spectroscopy works by analyzing the light coming from an object, whether reflected sunlight or emitted radiation, and breaking it down into its component wavelengths. Much like a prism separates white light into a rainbow, different chemical elements absorb and emit light at very specific wavelengths, creating unique fingerprints that allow astronomers to determine what distant objects are made of, without ever physically sampling them. When the VLT team pointed their spectrometers at 3I Atlas, they detected something unprecedented: 22 distinct emission lines, characteristic of neutral nickel atoms. 22 separate wavelengths at which nickel was absorbing and re-emitting sunlight in the comet's coma. This wasn't a subtle or marginal detection, it was a strong, unambiguous signature indicating that 3I Atlas was releasing significant quantities of nickel vapor into space. But when the astronomers looked for the corresponding signature of iron nickel's cosmic partner, formed through the same stellar processes and found together in every natural object ever analyzed, they found nothing. Complete absence, not a weak signal, not a marginal detection that might have been at the noise threshold of their instruments. Simply nothing. To understand why this was so remarkable, one needs to appreciate some basic cosmic chemistry. Heavy elements like nickel and iron are forged in the cores of massive stars through nuclear fusion processes that occur during the final stages of stellar evolution. When these stars explode as supernovae, they blast these newly created elements into interstellar space, where they eventually become incorporated into new star systems, planets, asteroids, and comets. The crucial point is that nickel and iron are created together in the same stellar furnaces through the same nuclear processes. They have similar atomic structures and similar chemical behaviors. In the natural world, in meteorites, in asteroids, in every comet ever analyzed, nickel and iron appear together in predictable ratios that reflect their cosmic abundance and formation history. Finding nickel without iron is like finding smoke without fire, or finding hydrogen without finding oxygen in water. It simply doesn't happen in natural processes. The VLT observations were repeated multiple times as 3I Atlas approached the Sun, and the nickel signature became stronger and more pronounced. Between July and August 2025, as the object moved from 3.8 to 0.8 astronomical units from the Sun, the nickel emission rate increased by a factor of 25. 25 times more nickel vapor being released over the course of just 1 month. This rate of increase was itself anomalous. Normal comets show gradual increases in activity as they approach the Sun, driven by the steady heating of their surfaces and the progressive sublimation of volatile materials. But a 25-fold increase in 1 month represented an exponential ramp-up for steeper than typical cometary behavior. By August 2025, 3I Atlas was releasing nickel at what the scientific literature described as an extreme rate. The production was higher than any comet ever observed at comparable distances from the Sun, and it was accelerating as the object continued its inward journey. The temperature problem made the observations even more puzzling. At the distances where 3I Atlas was being observed between 2.8 and 3.8 astronomical units, from the Sun's surface temperatures were far too low to vaporize metallic nickel directly. Nickel has a melting point of 1,455 degrees Celsius and a boiling point of 2,913 degrees Celsius. A comet's surface at 3 astronomical units from the Sun might reach a few dozen degrees. Above freezing in direct sunlight, perhaps 100 degrees Celsius at most. Nowhere near the temperatures required to turn solid nickel into vapor. The standard explanation proposed by planetary scientists was the nickel-carbonyl channel. This mechanism suggests that nickel isn't vaporizing directly from the comet's surface, but is instead trapped within carbon-bearing compounds that can sublime it at much lower temperature. When these compounds break down under solar radiation, they release the metal atoms along with other decomposition products. This explanation worked reasonably well for nickel detection, but it failed to explain the absence of iron. Iron forms similar carbonyl compounds under similar conditions. If the carbonyl mechanism was responsible for releasing nickel from 3I Atlas, it should also be releasing iron in similar quantities. The process isn't chemically selective. Both metals should appear in ratios roughly proportional to their abundances in the comet's composition, unless, of course, 3I Atlas contained virtually no iron to begin with. But this possibility raised its own set of problems. How does a natural object form with abundant nickel but negligible iron? What stellar or planetary formation process could create such a composition? The industrial parallel was uncomfortable to contemplate. On Earth, when humans want to produce pure nickel without iron contamination, we use a process called the Mond process or carbonyl process. Nickel ore is exposed to carbon monoxide at specific temperatures, causing the nickel to react and form nickel carbonyl, a volatile compound that can be separated from iron-rich residue. The nickel carbonyl is then decomposed at higher temperatures to recover pure nickel metal. This industrial process produces exactly what 3I Atlas was displaying: nickel emissions without corresponding iron signatures. The spectral characteristics of the comet's coma looked more like the output of a nickel refinery than the natural outgassing of a primitive solar system remnant. Dr. Avi Loeb, never shy about drawing uncomfortable conclusions from observational data, pointed out this parallel in several public statements and academic papers. He noted that while exotic natural chemistry might explain the observations, the simplest explanation that fit all the data involved some form of industrial nickel production or refinement process. The implications were staggering. If 3I Atlas was indeed producing refined nickel through artificial processes, it suggested technological capabilities far beyond anything in human experience. The object was estimated to mass at least 33 billion tons, roughly 6 million times more massive than the largest rockets ever built by humanity. If artificial, it represented engineering on a scale that dwarfed human industrial capacity by factors that made meaningful comparison almost impossible. But the nickel signature was just one piece of a larger puzzle. When combined with the statistically impossible trajectory, the unusual chemical composition dominated by carbon dioxide rather than water, the anomalous polarization characteristics, and the peculiar outgassing patterns observed by space telescopes. It formed part of a constellation of observations that challenged conventional explanations. The October 3rd flyby would have provided the opportunity to examine the nickel signature at much closer range than the VLT observations allowed. Mars-based spectrometers should have been able to detect not just the presence or absence of various elements, but their precise ratios, their distribution within the coma, and their variations over time as the object approached perihelion. Did the closer observations confirm the nickel without iron signature? Did they reveal additional elements or compounds that helped explain the unusual chemistry? Did they detect any evidence of the industrial processes that might account for such selective metal production? These questions had answers. In the data archives of the Mars spacecraft, in the spectrographic analyses conducted by NOMAD, Amiga, and other sensitive instruments, the chemical composition of 3I, Atlas, had been measured with unprecedented precision during its closest approach to human-made scientific instruments. But those answers remained classified, locked away in the same secure facilities where high-resolution images and thermal measurements were being analyzed by teams of scientists sworn to secrecy. The nickel signature represented the strongest single piece of physical evidence that 3I, Atlas, might be something other than a natural comet. It was a hard, measurable, reproducible observation that challenged basic assumptions about cosmic chemistry and suggested processes that didn't occur naturally anywhere else in the known universe. Whether the October 3rd observations confirmed or contradicted this signature could determine whether humanity was dealing with an extremely unusual natural object or with something that required entirely new categories of explanation. The data existed. The measurements had been made somewhere. People knew whether the nickel signature strengthened or disappeared under closer scrutiny. But they weren't talking. While individual aspects of 3I, Atlas, could potentially be explained through exotic but natural processes, the complete picture that emerged from months of observation presented a constellation of anomalies that strained conventional interpretation. When examined together, these 7 distinct characteristics formed a pattern that was becoming increasingly difficult to reconcile with purely natural origins. Anomaly 1, the extreme size based on brightness measurements and estimated albedo reflectivity. 3.1. Atlas appeared to be substantially larger than typical comets. While most comets have nuclei measuring a few kilometers across, 3I, Atlas, was estimated to have a diameter of approximately 10 to 15 kilometers, making it among the largest comet-like objects ever observed. More significantly, its estimated mass exceeded 33 billion tons, roughly equivalent to a metallic asteroid of similar size, rather than the lower-density ice-sand-rock mixture typical of comets. This mass estimate created its own puzzles. If 3I, Atlas, was indeed composed primarily of the carbon dioxide ice detected by spectroscopic observations, achieving such high mass would require a nucleus substantially larger than optical observations suggested. If it was composed of denser materials, rock, metal, or some combination that would explain the mass but contradict the spectroscopic evidence for abundant volatile materials. Anomaly 2, the forward jet. When the Hubble Space Telescope captured detailed images of 3I, Atlas in July 2025, astronomers immediately noticed something unusual about its appearance. Rather than displaying the typical comet morphology of a bright coma with a tail streaming away from the Sun, 3.1, Atlas showed a prominent jet extending ahead of its nucleus pointing toward the Sun, rather than away from it. This forward jet was approximately 10 times longer than it was wide, suggesting a highly collimated stream of material rather than the diffuse outgassing patterns typical of natural comets. The jet maintained its structure over several weeks of observation, indicating that whatever was producing it was operating consistently rather than episodically. Forward jets can occur naturally in comets when subsurface ice deposits are exposed to sunlight and begin venting material in specific directions. But such jets are typically short-lived phenomena that appear and disappear as the nucleus rotates. and different surface areas are exposed to solar heating. The persistence and structure of 3I, Atlas's forward jet, was more reminiscent of controlled propulsion than natural outgassing. Anomaly 3. The delayed tail formation for weeks after the Hubble observations revealed the forward jet. 3.1. Atlas failed to develop the characteristic tail that astronomers expected to see. As it approached the Sun, normal comets begin showing tails when they reach approximately 3 astronomical units from the Sun, as solar wind pressure becomes strong enough to push gas and dust away from the nucleus. 3.1. Atlas remained tailless until late August 2025, when a faint tail finally appeared. Even then, the tail was notably weak compared to the object's overall brightness and activity level. This delayed tail formation suggested either unusual composition or unusual geometry that didn't conform to standard cometary models. Anomaly 4. The carbon dioxide dominant spectroscopic analysis by NASA's James Webb Space Telescope and other advanced instruments revealed that 3I, Atlas's coma, was composed of approximately 95% carbon dioxide and only 5% water vapor. This represented an 8-to-1 ratio of carbon dioxide to water, the reverse of what is typically observed in solar system comets, which tend to be water-dominated. While carbon dioxide-rich comets do exist, particularly among those originating from the outer solar system, the extreme dominance of CO2 in 3I, Atlas was unusual. More significantly, carbon dioxide sublimates transforms directly from solid to gas at much lower temperatures than water ice, which explained why 3I, Atlas, had become active at the relatively large distance of 4. For astronomical units from the Sun. From a practical engineering perspective, carbon dioxide would be an excellent choice for a spacecraft propulsion system. Using cold gas thrusters, it's stable, easy to store, and provides predictable thrust characteristics when released through nozzles. Whether this was relevant to 3I, Atlas's composition was a matter of interpretation. Anomaly 5. The extreme negative polarization polycritim observations measurements of how light becomes polarized when reflected from an object's surface revealed that 3I, Atlas, exhibited extreme negative polarization characteristics. Unlike any comet previously studied, polarization measurements provide information about surface texture, composition, and the size and shape of dust grains in the surrounding coma. Negative polarization can occur naturally, under certain conditions, typically involving very small particles or specific mineral compositions, but the degree of negative polarization exhibited by 3I, Atlas, was far outside the normal range for cometary objects, suggesting either highly unusual surface properties or the presence of artificially manufactured materials with specific optical characteristics. Anomaly 6. The statistically impossible trajectory as discussed previously. The probability of 3I, Atlas, randomly achieving its observed trajectory, nearly aligned with the ecliptic plane and timed for close encounters with both Mars and Jupiter, was approximately 0.5%, or roughly 1 in 200,000. While not impossible, such odds prompted serious consideration of whether the trajectory might have been deliberately calculated rather than randomly determined. The trajectory also happened to be nearly optimal for a reconnaissance mission designed to survey multiple worlds within our solar system. The retrograde orbit opposite to planetary motion meant that encounters occurred with relative velocities that were ideal for extended observation periods. Anomaly 7. The WOW signal meant perhaps the most speculative of the anomalies, but nonetheless mathematically intriguing, was the correlation between 3I, Atlas's calculated position in 1977, and the famous WOW signal detected by the Big Ear radio telescope. On August 15, 1977, the telescope detected a strong, narrowband radio signal at 1,420 MHz, the hydrogen line frequency, that lasted for 72 seconds and was never detected again. When astronomers traced 3I, Atlas's trajectory backward to 1977, they found that the object would have been located approximately 600 astronomical units from Earth. in a position just 9 degrees away from the WOW signal's apparent origin point. The probability of this alignment being coincidental was approximately 0.6%. If 3I Atlas had transmitted the WOW signal as a form of active scanning or communication, it would have required power output of approximately 0.5 to 2 gigawatts substantial, but not impossible for an advanced technological system. The signal's characteristics short duration, specific frequency, and Doppler shift indicating an approaching source were consistent with what might be expected from a probe conducting systematic surveys of nearby star systems individually. Each of these 7 anomalies could potentially be explained through exotic but natural processes. Unusual formation environments, statistical coincidences, poorly understood cometary physics, and observational uncertainties could account for any single strange characteristic. But when all 7 anomalies appeared in the same object, the cumulative improbability became staggering. If each anomaly had a 1% chance of occurring, naturally a generous estimate for most of them, the probability of all 7 appearing together would be 1 in 1014, 1 in 100 trillion. Dr. Avi Loeb had developed a classification system for potentially artificial objects, ranging from 0 definitely natural to 10 definitely artificial and potentially hostile. Based on the 7 anomalies, he assigned 3I Atlas a rating between 2 and 4, not definitively artificial, but anomalous enough to warrant serious consideration of non-natural explanations. The October 3rd observations should have provided crucial data for resolving these anomalies. High-resolution imaging could reveal whether the object's structure was consistent with natural formation or showed evidence of artificial construction. Detailed spectroscopy could confirm or refute the unusual chemical signatures. Thermal measurements could detect any evidence of internal energy sources or unusual heat distribution patterns. Most importantly, the combination of 7 different spacecraft with complementary instrument suites should have provided a comprehensive, multifaceted analysis that could definitively characterize 3I Atlas as either an extremely unusual natural object or something requiring entirely new categories of explanation. The data from these observations existed in the secure archives of multiple space agencies. Scientists with appropriate clearances were analyzing images, spectra, and measurements that could resolve the central question about 3I Atlas's nature and origin. But nearly a week after the closest approach, that analysis remained locked away from public scrutiny, accessible only to those with both the technical expertise and the security permissions to examine humanity's most detailed observations of its most unusual interstellar visitor. As the silence from space agencies stretched into its second week, attention began focusing on an event that would occur far from the prying eyes of Earth-based telescopes. 3I Atlas's passage through perihelion. On October 29, 2025, the interstellar visitor would reach its closest approach to the Sun at a distance of 1.36 astronomical units, about 203 million kilometers, just inside the orbit of Mars and just outside the orbit of Earth. For any comet, perihelion represents the moment of maximum activity. The intense solar radiation reaching the object's surface drives volatile materials to sublime it at their highest rates, creating the spectacular comas and tails that make comets visible to the naked eye from Earth. For 3I Atlas, already showing unusual activity at much greater distances, perihelion promised to be either a moment of spectacular natural display or something else entirely. But there was a critical problem with observing this crucial event from Earth's perspective. 3I Atlas would be completely hidden behind the Sun during its perihelion passage. The geometry was unavoidable as the comet approached its closest point to the Sun. It would appear to move closer and closer to the Sun's position in Earth's sky, until it disappeared entirely behind the solar disk. This solar occultation would last for several weeks, from mid-October through late November, encompassing not just the perihelion passage itself, but the entire period when 3I Atlas would be at its most active. When the object finally emerged from behind the Sun in late November or early December, it would be receding from perihelion. heading back toward the outer solar system and eventually toward interstellar space. The timing couldn't have been more frustrating for astronomical observation. Perihelion was precisely when comets revealed their true nature most clearly. The intense solar heating drove the sublimation of materials that remained frozen and inactive at greater distances. Surface features became visible as different areas responded differently to thermal stress. Structural weaknesses often caused comets to fragment at perihelion, sometimes splitting into multiple pieces that revealed internal composition and structure. For 3I Atlas, with its constellation of unusual characteristics, perihelion represented the best opportunity to determine whether it was an extremely unusual but natural comet or something requiring entirely different categories of explanation. If it was natural, perihelion should trigger massive outgassing, dramatic brightening, possible fragmentation, and the development of a spectacular tail as solar wind pressure reached its maximum intensity. If it was something else, if there was any validity to the artificial origin hypotheses that had been circulating in astronomical communities, perihelion might reveal very different behavior patterns. The occultation period raised uncomfortable possibilities. In orbital mechanics, perihelion represents the optimal point for major trajectory changes. When a spacecraft is deep in a gravitational well, small changes in velocity produce large changes in orbital energy. This principle, known as the Oberth effect, is routinely used by mission planners to maximize the efficiency of spacecraft maneuvers. If 3I Atlas wanted to change its trajectory, if it intended to decelerate and become gravitationally bound to the Sun, rather than continuing on its current hyperbolic escape, path perihelion would be the most logical place to execute such a maneuver. A reverse Oberth maneuver performed at closest approach could potentially capture the object into an elliptical solar orbit with minimal energy expenditure. The timing and geometry would be perfect for concealing such a maneuver. Hidden behind the Sun from Earth-based observation, 3I Atlas could fire engines, deploy solar sails, or execute whatever propulsion system it might possess without detection. The thermal and radiation environment around perihelion would mask most propulsion signatures, and the solar interference would prevent radio observations that might detect artificial signals. More troubling still was the possibility of payload deployment. If 3I Atlas was some form of mothership carrying smaller probes designed for inner-system reconnaissance, the retrograde orbit made perihelion the optimal deployment point. Small probes released with minimal velocity at perihelion could intercept Earth's orbit with relatively little energy expenditure, taking advantage of the opposite orbital motions to achieve interception courses. These scenarios sounded like science fiction, but they were mathematically sound applications of orbital mechanics principles. Dr. Loeb had published papers outlining exactly how such maneuvers could be executed, and why the timing and geometry of 3I Atlas's perihelion passage made it particularly suitable for such activities. The alternative that 3I Atlas would behave like a normal comet during perihelion was certainly more likely from a conventional scientific perspective. The object should brighten dramatically as its surface heated to maximum temperatures. It should develop spectacular outgassing patterns as subsurface ices were exposed and began venting. It should possibly fragment if thermal stresses exceeded the structural integrity of its nucleus. When it emerged from solar occultation in late November, astronomers expected to see a transformed object brighter, more active, possibly split into multiple components, but still recognizably following the same hyperbolic trajectory that would carry it back to interstellar space. Multiple observatories around the world were preparing for the moment when 3I Atlas would reappear. From behind the Sun, the European Southern Observatory's very large telescope, the Atacama Large Millimeter, Submillimeter Ray, and dozens of other major facilities had reserved observation time to capture the first images of the post-perihelion object. Space agencies were also positioning assets for the re-emergence observations, while the government shutdown continued to hamper NASA operations. ESA was coordinating with ground-based observatories to ensure comprehensive coverage. when 3I Atlas became visible again. Even China's space program, silent since October regarding their Mars observations, was reportedly preparing ground-based telescopes for post-perihelion monitoring. The intensity of this preparation suggested that the October 3rd Mars flyby observations had revealed something significant enough to warrant careful monitoring of 3I Atlas's subsequent behavior. If the Mars encounter had simply confirmed normal cometary activity, there would be less urgency about tracking the object's post-perihelion characteristics. But if the Mars observations had detected anomalous structural features that didn't fit natural models, unusual thermal signatures, or behavior patterns that suggested artificial systems, then perihelion became a crucial test. Would the object continue behaving anomalously under the extreme conditions of closest solar approach? Would it maintain structural integrity that natural comets couldn't achieve? Would it emerge from solar occultation on a different trajectory than it entered? The October 3rd data that remained locked in secure facilities presumably contained information that could help predict what might happen during the hidden perihelion passage. High-resolution images could reveal structural details that would indicate whether the object was likely to survive perihelion intact. Spectroscopic data could identify volatile components that would become active under intense solar heating. Thermal measurements could reveal internal heat distribution patterns that might affect the object's response to external heating. But without access to that data, the scientific community was left to wait and wonder. The perihelion passage would occur in secret, behind the sun, invisible to human observation. Whatever happened during those critical hours when 3I Atlas experienced maximum solar heating would remain unknown until the object reappeared weeks later. By then, it might be too late to understand what had occurred. If 3I Atlas emerged on a different trajectory, deployed smaller objects, or exhibited post-perihelion characteristics that couldn't be explained by natural processes, humanity would know something significant had happened but would have missed the actual event. 22 days remained until perihelion. 22 days during which the silence from space agencies continued, during which the October 3rd observations remained classified, and during which one of the most important astronomical events in human history approached its hidden climax. As October progressed and the silence regarding 3I Atlas observations continued, the ongoing United States government shutdown began to significantly complicate the situation. What had started as a routine congressional budget dispute was now interfering with one of the most important astronomical investigations in human history. The shutdown had begun on October 1, 2025, when Congress failed to pass appropriations bills for the new fiscal year. As with previous government shutdowns, NASA was among the federal agencies most severely affected. More than 15,000 NASA employees, 83% of the agency's workforce, had been furloughed, leaving only essential personnel to maintain critical operations and ensure the safety of astronauts aboard the International Space Station. At the Jet Propulsion Laboratory in Pasadena, California, where most NASA Mars missions are managed, only skeleton crews remained on duty. The sophisticated data processing pipelines that normally handled the constant flow of information from Mars orbiters and rovers were operating at minimal capacity. Routine science operations that typically proceeded smoothly were now subject to bureaucratic complications and staffing limitations. Under normal circumstances, the Mars Reconnaissance Orbiter's high-rise images would be processed and released to the public within days of acquisition. The complex but well-established workflow involved multiple teams, engineers who verified data integrity, scientists who provided geological context, and public affairs specialists who prepared explanatory materials for media release. With most of these personnel furloughed, the normal data flow had slowed to a trickle. Similar problems affected Perseverance operations. While the rover continued its automated surface activities, the core systems were designed to operate independently. For extended periods, the analysis and release of its observations required human oversight that was no longer available at full capacity. The timing was particularly unfortunate given the significance of the October 3rd observations. Under normal staffing levels, the Mars flyby data would have received priority processing, with teams working around the clock to analyze the unprecedented observations of an interstellar visitor. Instead, the data sat in processing queues, waiting for furloughed employees to return to work. But the shutdown explanation, while clearly relevant to NASA's silence, failed to account for the similar reticence from other space agencies. The European Space Agency operated entirely independently of US budget disputes. ESA's funding came from member nations of the European Union through entirely separate mechanisms. The agency's facilities in Germany, France, Spain, and other European countries were fully staffed and operating normally. Yet ESA's initial release on October 7th had been notably limited, showing only basic images of 3I, Atlas with minimal analysis or interpretation. The agency's normally comprehensive press releases, which typically included detailed scientific context and multiple expert perspectives, had been replaced by a brief technical summary that raised more questions than it answered. China's silence was even more difficult to explain through shutdown complications. The China National Space Administration answered directly to the Chinese Communist Party and operated under an entirely different governmental structure. CNSA had no furloughed employees, no budget disputes, and no bureaucratic obstacles preventing normal data release procedures for 4 years. Tianwen-1 had maintained an impressive pace of public outreach, releasing an average of 12 images per day from Mars orbit. The Chinese space program had consistently used Mars mission data for international prestige purposes, demonstrating technological capabilities and scientific achievements to global audiences. The complete absence of any Tianwen-1 observations of 3I, Atlas, represented a dramatic departure from this established pattern. If the Chinese orbiter had captured routine images showing normal cometary activity, those images would almost certainly have been released immediately, potentially beating American and European agencies to the publicity advantage of first detailed interstellar object observations. The fact that CNSA was maintaining silence despite obvious opportunities for positive publicity suggested either that their observations had failed entirely, which seemed unlikely given the spacecraft's proven capabilities, or that what they had observed required careful consideration before public release. The United Arab Emirates faced no shutdown complications either. The UAE's Hope orbiter was managed by the Mohammed bin Rashid Space Center in Dubai, with full staffing and normal operations. The Emirates' Mars mission had positioned itself as a contributor to international Mars science, regularly sharing atmospheric observations and collaborating with researchers worldwide. Yet Hope's silence regarding 3I, Atlas, mirrored that of the larger space agencies, suggesting coordination that transcended individual national concerns about data release timing. The shutdown was also affecting planned follow-up observations. NASA's potential redirection of the Juno spacecraft. For a March 2026 encounter with 3I, Atlas remained frozen in bureaucratic limbo. The trajectory change needed to position Juno for the Jupiter flyby required approval from senior NASA administrators, most of whom were furloughed. Critical decisions about spacecraft operations were being delayed indefinitely, while budget negotiations continued in Congress more immediately. The shutdown was hampering coordination between NASA and other agencies for the anticipated re-emergence observations when 3.1 Atlas would become visible again after its passage behind the Sun. International astronomical coordination typically required extensive communication between agencies, sharing of observation plans, and coordination of ground-based telescope scheduling. With most NASA personnel unavailable, these coordination efforts were proceeding slowly or not at all. The irony was painful. Just as humanity achieved its best-ever observations of an interstellar visitor, bureaucratic complications were preventing normal scientific processes from operating effectively. The data existed captured by functioning spacecraft with operating instruments, but the human infrastructure needed to analyze and release that data was partially paralyzed by political disagreements that had nothing to do with space exploration. Some observers suggested that the shutdown might actually be providing convenient cover for agencies that wanted additional time to analyze unusual observations without public pressure for immediate release. If the October 3rd data had revealed something unexpected, something that required careful verification or coordination between multiple agencies, the shutdown offered a plausible explanation for delays that might otherwise seem suspicious. But this theory required assuming that ESA, CNSA, and the UAE were all cooperating in using NASA's domestic political problems as cover for their own reticence. While not impossible, such coordination would represent an unprecedented level of international space agency cooperation. On matters of data release timing, more likely, the shutdown was simply making a complex situation worse. The October 3rd observations had probably revealed something that required careful analysis and interagency consultation regardless of staffing levels. The shutdown was slowing that analysis and consultation process, extending the period during which the astronomical community and general public would have to wait for answers. As October progressed toward the crucial perihelion passage, the shutdown showed no signs of resolution. Congressional negotiations remained deadlocked over unrelated fiscal issues, with no clear timeline for reopening government agencies. NASA's critical role in coordinating international observations of 3I atlases post-perihelion behavior was being compromised by domestic political dysfunction. The situation highlighted how Earth-based political complications could interfere with humanity's ability to investigate cosmic phenomena that transcended national boundaries. Whether 3I Atlas was a natural comet or something more exotic, its investigation required international scientific cooperation that was being hampered by the shutdown's effects on one of the world's largest space agencies. Meanwhile, the clock continued counting down toward perihelion. In secure facilities where skeleton crews analyzed classified observations, people were examining data that could determine whether humanity was dealing with an unusual natural visitor or something that challenged basic assumptions about our place in the universe. But those answers remained locked away, inaccessible to the broader scientific community that might help interpret them, delayed by bureaucratic complications that seemed trivial compared to the cosmic significance of what might have been discovered orbiting Mars on October 3, 2025. As the second week of silence stretched on, attention in the scientific community increasingly focused on the single most troubling piece of evidence about 3I Atlas's nature, the industrial-grade nickel production that defied every known natural process in cosmic chemistry. The detection had been made by the Very Large Telescope during systematic observations between July and August 2025. But its implications became more disturbing as additional data emerged from other observatories. Not only was 3I Atlas producing massive quantities of purified nickel vapor, but it was doing so through processes that matched human industrial techniques more closely than any natural phenomenon ever observed. Dr. Elena Vasquez, a specialist in cosmic chemistry at the Max Planck Institute for Astronomy, had been analyzing the VLT spectroscopic data since its release in September. Her conclusions, published in a preliminary report that had circulated quietly through astronomical communities, were stark. The nickel emission characteristics of 3I Atlas are consistent with industrial carbonyl chemistry processes. No natural mechanism currently known to science can produce such selective metal purification. In the low-temperature environment of the outer solar system, the technical details were unambiguous. The VLT had detected 22 distinct emission lines characteristic of neutral nickel atoms, at wavelengths ranging from 338.9 to 676.8 nanometers. This represented a comprehensive spectral signature indicating that 3I Atlas was releasing nickel vapor across a broad range of energy states, suggesting active, ongoing production rather than the simple sublimation of surface deposits. Equally significant was what the spectrometers had not detected. Iron, nickel's cosmic partner, should have appeared at wavelengths of 385.9 for 138.4 and 527.0 nanometers if present in normal cosmic abundances. The VLT's sensitivity was more than adequate to detect iron at these wavelengths. The same instrument had successfully identified both nickel and iron in other comets, observed under similar conditions. But in 3I Atlas, the iron signatures were completely absent. Not weak, not marginal, not at the threshold of detection, simply absent. The temperature constraints made this selectivity even more remarkable. At distances of 2.8 to 3.8 astronomical units from the Sun, where the observations were made, 3I Atlas's surface temperature would have reached perhaps 100 to 250 Kelvin, 73 to minus 23 degrees Celsius. These temperatures were sufficient to sublimate carbon dioxide, ice, and other volatile compounds, but nowhere near the 1728 Kelvin, 1455 degrees Celsius required to melt metallic nickel, much less the 3186 Kelvin to 1913 degrees Celsius needed for nickel vaporization, the proposed carbonyl channel mechanism where metals become incorporated into carbon-bearing compounds that can sublimate at lower temperatures provided a potential natural explanation, but it failed to account for the selective absence of iron. Iron carbonyl compounds form under the same conditions as nickel carbonyls and should decompose to release iron vapor alongside nickel vapor. Unless the carbonyl formation process was being artificially controlled on Earth. The industrial production of high-purity nickel relies on precisely this chemistry. The Mond process, developed in the 1890s and still used today, exposes nickel-bearing ores to carbon monoxide at temperatures around 50 to 80 degrees Celsius. Under these conditions, nickel preferentially forms nickel tetracarbonyl carbon monoxide 4, a volatile compound that can be separated from iron-rich residues through distillation. The nickel tetracarbonyl is then heated to around 180 degrees Celsius, causing it to decompose and release pure nickel metal along with carbon monoxide gas. The carbon monoxide can be recycled back into the process, creating a closed-loop system for extracting and purifying nickel from mixed metal ores. The temperatures involved in this industrial process 50180 degrees Celsius were entirely consistent with the thermal environment of 3I Atlas at its observed distances from the Sun. If the object contained both nickel-bearing materials and a source of carbon monoxide which could come from carbon dioxide photolysis under solar radiation, the Mond process could operate naturally. But natural operation of the Mond process required specific engineering to achieve the selective purification that 3I Atlas was displaying. The process worked in human industry because it was carefully controlled. Specific temperatures, pressures, and chemical environments were maintained to favor nickel carbonyl formation over iron carbonyl formation. Random natural processes shouldn't exhibit such selectivity. Dr. Vasquez's analysis had identified additional troubling details in the spectroscopic data. The nickel emission lines showed Doppler shifts that indicated the vapor was being released at velocities of approximately 2 to 3 kilometers per second, much faster than typical cometary outgassing, which usually produces velocities of 0.5 to 1 kilometer per second. Higher velocity outgassing could result from more energetic sublimation processes, but it could also indicate controlled release through nozzles or vents designed to accelerate the gas flow. The velocity profiles were more consistent with engineered systems than with the random thermal processes that drove normal cometary activity. Even more disturbing was the temporal pattern of nickel production, rather than the gradual increase expected from natural solar heating. 3I Atlas showed exponential ramp-up in nickel emission as it approached the Sun. Between July and August, the production rate increased by a factor of 25, far steeper than the gradual temperature increases caused by orbital mechanics. This suggested that nickel production was being driven by some internal process that was ramping up faster than solar heating alone could account for. Either 3I Atlas contained internal heat sources that were becoming more active as it approached perihelion. or it contained systems that were actively responding to its changing solar environment. The spectroscopic data had one more troubling characteristic. The nickel emissions showed temporal variations that appeared almost periodic. Rather than steady production, 3I Atlas seemed to be releasing nickel impulses or cycles, with production rates varying by factors of 2 to 3 over periods of several hours. Natural outgassing driven by solar heating should be relatively steady, varying only with the rotation period of the nucleus as different surface areas were exposed to sunlight. But 3I Atlas's rotation period, estimated from brightness variations, was approximately 7.3 hours. The nickel production cycles occurred over much shorter time scales 2 to 4 hours and didn't correlate with the expected rotation period. This suggested that nickel production was being controlled by internal processes that operated independently of simple solar heating patterns. Whether those processes were exotic natural phenomena or artificial systems remained an open question, but the temporal signatures were more consistent with engineered controls than with passive thermal responses. The implications were staggering. If 3I Atlas was indeed operating industrial-scale nickel purification processes, it represented technological capabilities that dwarfed human industrial capacity. The object was producing nickel at rates exceeding several tons per day, more than most terrestrial nickel refineries. Scaled up to the estimated 33 billion ton mass of 3I Atlas, the total nickel content could exceed the entire known nickel reserves on Earth. If artificial, the object represented not just advanced technology, but access to material resources on scales that transformed basic assumptions about what interstellar engineering projects might involve. The October 3rd Mars flyby observations should have provided crucial additional data about the nickel production process. Mars-based spectrometers could examine the chemistry at much closer range than ground-based telescopes, potentially detecting trace elements, molecular compounds, or isotopic ratios that could distinguish between natural and artificial processes. Did the closer observations reveal additional evidence of carbonyl chemistry? Were there other industrial processes at work alongside nickel purification? Did the spectroscopic signatures become more or less artificial looking under higher resolution analysis? These questions had definitive answers locked away in the classified observation archives. Somewhere, scientists with appropriate security clearances were examining spectroscopic data that could determine whether humanity was observing the most sophisticated industrial chemistry ever encountered, or whether exotic natural processes could account for the unprecedented selectivity of 3I Atlas's metal production. But those answers remained inaccessible to the broader scientific community that might help interpret them, trapped behind walls of official secrecy. That seemed increasingly inadequate to the cosmic significance of what might have been discovered. Among the 7 anomalies associated with 3I Atlas, none was as speculative or as potentially significant as its possible connection to the most famous unsolved mystery in the search for extraterrestrial intelligence. The WOW signal detected on August 15, 1977. The Big Ear Radio Telescope at Ohio State University had been conducting a systematic search for artificial radio signals from space as part of SETI's search for extraterrestrial intelligence operations. The telescope automatically scanned different portions of the sky, recording signal strength across various frequencies and looking for anything that might indicate non-natural origins. At 23:16 Eastern Standard Time on that August evening, the telescope detected something extraordinary, a strong, narrowband radio signal at 1420.405 MHz, very close to the hydrogen line frequency that many SETI researchers considered the most logical choice for interstellar communication attempts. The signal lasted exactly 72 seconds, the maximum duration that Big Ear's scanning pattern could observe any single point in the sky. It showed a characteristic intensity profile that started weak, peaked in the middle, and faded out, exactly what would be expected from a point source in space as the Earth's rotation carried the telescope's beam across it. Most significantly, The signal was blue-shifted, indicating that its source was moving toward Earth at a velocity of approximately 10 kilometers per second. Astronomer Jerry Eman, reviewing the computer printouts the following day, was so struck by the signal's characteristics that he circled the alphanumeric code representing its intensity and wrote "Wow" in the margin. The notation gave the detection its popular name and marked the beginning of nearly 5 decades of unsuccessful attempts to explain or repeat the observation. Despite numerous follow-up observations using the same telescope and others around the world, the WOW signal was never detected again. No natural astronomical phenomenon could account for its characteristics. No terrestrial source could explain its frequency and duration. It remained, in the words of SETI researchers, best candidate for an artificial extraterrestrial signal ever detected. The connection to 3I Atlas emerged from routine orbital calculations performed by astronomers tracking the interstellar visitor's trajectory. When they computed where 3I Atlas would have been located in August 1977, the results were startling. The object would have been approximately 600 astronomical units from Earth, roughly 90 billion kilometers, or about 20 times farther from the Sun than Pluto. At that distance, 3I Atlas would have been completely invisible to 1970s-era telescopes, an undetectable speck moving slowly through the outer darkness of our solar system, but its calculated position in the sky was separated by only 9 degrees in right ascension and 8 degrees in declination from the WOW signal's apparent origin point in the constellation Sagittarius. 9 degrees out of 360 degrees around the entire sky represented a remarkably close alignment. The probability of this being purely coincidental was approximately 0.6%, 6 chances in 1,000, or roughly 1 in 167. If 3I Atlas had transmitted the WOW signal, the power requirements could be calculated from basic physics principles at a distance of 600 astronomical units. Producing a signal detectable by big ears receivers would have required transmission power between 0.5 and 2.0 gigawatts, substantial, but well within the capabilities of a large nuclear power plant on Earth. For an object with the estimated mass and size of 3I Atlas, such power output was theoretically feasible if it contained appropriate energy generation systems. Whether those systems could be natural, perhaps involving radioactive decay or some exotic stellar remnant material, or would necessarily be artificial, remained an open question. The timing made the connection even more intriguing. In 1977, 3I Atlas would have been beginning its approach toward the inner solar system, still decades away from its closest encounters with Mars and Jupiter, but already close enough to begin detailed reconnaissance of our solar system's structure. If the object was some form of interstellar probe, 1977 would represent a logical time to begin active scanning operations. Radio surveys could map planetary positions, identify asteroid belt structure, and potentially detect any artificial radio emissions from an emerging technological civilization on Earth. The WOW signal's characteristics were consistent with such a survey beam. The 72-second duration matched the maximum observation time possible with Big Ear's scanning pattern, suggesting that the signal was continuous but only briefly intersected Earth's position. The narrow bandwidth and specific frequency suggested an artificial, engineered transmission rather than natural astronomical phenomena. Most tellingly, the signal was never repeated despite decades of follow-up observations. This was puzzling if the source was some ongoing natural phenomenon, or a deliberate communication attempt that would presumably be retransmitted. But it made perfect sense if the signal was a single scanning pulse from a probe conducting a wartime survey of our solar system. Dr. Avi Loeb had published detailed calculations showing how an interstellar probe could use radar-like pulses to map planetary systems during approach. Such a probe would emit powerful radio bursts while sweeping through different directions, analyzing the return echoes to identify solid objects, measure their distances and sizes, and map orbital structures. Earth would occasionally intersect these scanning beams purely by geometric chance. receiving brief but intense radio signals that would appear and disappear as the probe's beam swept past. The detection pattern would be sporadic and unpredictable from Earth's perspective, even though the scanning was systematic from the probe's perspective. If 3I Atlas had conducted such a radar survey in 1977 and detected clear signatures of a planetary system with multiple worlds in stable orbits, including one in the habitable zone around its star, the probe might have adjusted its trajectory. To enable closer investigation, the mathematics supported this possibility. Small trajectory adjustments made at 600 astronomical units could result in significantly different arrival dates and approach geometries in the inner solar system. If 3I Atlas had accelerated slightly after its 1977 reconnaissance, it could have advanced its arrival at Mars from a natural trajectory that might have occurred years later. This would explain both the wow signal connection and the statistically improbable trajectory that brought 3I Atlas to optimal observation positions for Mars and Jupiter encounters, rather than random cosmic coincidence. The trajectory could represent deliberate course corrections made after initial reconnaissance identified our solar system as worthy of detailed investigation. The speculation raised obvious questions about 3I Atlas's subsequent behavior. If it had already detected Earth's technological civilization through radio emissions visible by 1977, what would be its purpose in approaching for closer observation? Pure scientific curiosity? Evaluation of humanity's technological development? Preparation for some form of contact or intervention? The questions were impossible to answer without additional data, but they provided context for interpreting the October 3rd Mars flyby observations. If 3I Atlas was some form of probe that had been actively surveying our solar system for nearly 5 decades, its behavior during close spacecraft encounters might reflect awareness of human technological capabilities. Did the object respond to the presence of 7 spacecraft observing it simultaneously? Did it modify its activity patterns or outgassing behavior in ways that suggested recognition of artificial observers? Did it emit any signals, radio, optical, or otherwise, that could be interpreted as acknowledgement or communication attempts? These possibilities seemed far-fetched from conventional scientific perspectives, but they were logically consistent with the hypothesis that 3I Atlas represented advanced technology rather than a natural comet. If true, the October 3rd observations might have captured humanity's first direct evidence of extraterrestrial intelligence. The data existed somewhere in classified archives. High-resolution images, spectroscopic analyses, radio observations, and other measurements that could reveal whether 3I Atlas showed any signs of artificial behavior during its closest approach to human-made scientific instruments, whether those observations supported or contradicted the wow signal connection remained unknown to the scientific community and general public. But for nearly 2 weeks, the silence from space agencies suggested that whatever had been observed required careful consideration before being shared with the world. The wow signal had remained unexplained for nearly 5 decades. If 3I Atlas provided the answer to that enduring mystery, it would represent one of the most significant discoveries in human history. Not just the detection of extraterrestrial intelligence, but evidence that such intelligence had been observing and investigating our solar system for decades before making direct contact. By October 20, 2025, the silence regarding 3I Atlas had stretched beyond 2 weeks, evolving from curious to concerning to genuinely unprecedented in the history of space exploration. While government shutdowns and bureaucratic complications could explain some delays, the coordinated reticence for independent space agencies suggested something far more significant than routine data processing problems. The astronomical community had begun to fracture into competing camps of interpretation. Conservative scientists maintained that the delays were certainly due to technical difficulties, government shutdowns, or the natural caution that accompanied analysis of such unusual observations. They argued that extraordinary claims required extraordinary evidence, and that space agencies were simply exercising appropriate scientific rigor before making public statements about an object that had already generated considerable speculation. But growing numbers of researchers were becoming convinced that the silence itself was the most significant datum available. Dr. Sarah Chen, a planetary scientist at the University of California, Berkeley, who had been tracking the situation closely, published an analysis that was circulating widely through informal networks. In 30 years of studying space mission data release patterns, I have never observed this level of coordination between competing agencies. The only precedent for such behavior would be a discovery so significant that it requires consultation at the highest levels of government before public release. The timing was becoming increasingly critical as 3I, Atlas, approached its perihelion passage on October 29th. In just 9 days, the interstellar visitor would reach its closest approach to the Sun and disappear behind the solar disk, invisible to Earth-based observation for several weeks. Whatever was going to be revealed about the October 3rd Mars flyby observations would need to happen soon, or the opportunity would be lost entirely. More troubling was the possibility that space agencies were deliberately waiting for the perihelion occultation to provide cover for continued secrecy. Once 3I, Atlas disappeared behind the Sun, any unusual behavior during its most active phase would be unobservable from Earth. If the object was going to do something unexpected, change trajectory, deploy smaller objects, or exhibit non-cometary behavior, perihelion would provide perfect concealment. The European Space Agency had maintained complete silence since their October 7th release of basic images showing 3I, Atlas, as a slightly fuzzy white dot. No follow-up analysis, no additional spectroscopic results, no interpretation of the observations they had characterized as requiring weeks or months of additional study. NASA's silence could still be partially attributed to the government shutdown, though even skeleton crews should have been capable of releasing routine scientific observations. If that's what the October 3rd data contained, the agency's public affairs staff had been fielding increasingly pointed questions from science journalists, but responses remained limited to variations of data. Analysis is ongoing, and results will be shared when available. China's continued silence was perhaps most telling. The China National Space Administration had built its Mars program reputation on rapid, comprehensive data release. Their failure to publish even routine images from Tianwen-1's observations represented a complete break from 4 years of established practice. Either their spacecraft had failed entirely to observe 3I, Atlas, which seemed unlikely given advanced planning and the object's predictable trajectory, or their observations had revealed something that required careful consideration. At the highest levels of government, the UAE's silence was equally significant. The Emirates Mars mission had positioned itself as a collaborative, transparent contributor to international Mars science. Their failure to share Hope orbiter observations suggested coordination with the larger space agencies that transcended normal scientific publication. Protocols. Amateur astronomical communities had attempted to fill the information void through their own observations, but ground-based telescopes lacked the resolution and sensitivity needed to detect the subtle features that spacecraft observations could reveal. 3.1. Atlas remained visible through large amateur telescopes as a faint, fuzzy object with a developing tail, but detailed analysis required the sophisticated instruments that only space agencies possessed. Some amateur observers reported unusual variations in 3I, Atlas's brightness and apparent structure, but these observations were difficult to verify and could easily be attributed to atmospheric effects, instrumental limitations, or observational bias. Without professional confirmation, amateur reports contributed to speculation rather than scientific understanding. The speculation had grown increasingly elaborate as the silence continued. Online forums dedicated to space exploration and SETI research buzzed with theories ranging from mundane technical explanations to exotic scenarios involving first contact, protocols, and international agreements to suppress potentially destabilizing discoveries. Government shutdown impacts were clearly affecting NASA's ability to coordinate with international partners for post-perihelion observations. Critical planning meetings for the anticipated re-emergence observations in late November were being delayed or conducted with minimal American participation. The timing couldn't have been worse for an event that required careful international coordination. But the shutdown was also creating opportunities for unofficial information leaks. Furloughed NASA employees, frustrated by the political dysfunction that was interfering with their scientific work, had begun speaking more freely in informal settings about their experiences with the 3I Atlas observations. None of these conversations had produced definitive revelations, but the pattern of hints was consistent. Something unusual had been observed on October 3rd, something that required additional analysis and interagency consultation before public release. The furloughed employees couldn't provide details. Most didn't have access to the actual data, but their demeanor suggested that routine cometary observations wouldn't require such extraordinary secrecy. International astronomical organizations were beginning to express concern about the extended delay in data release. The International Astronomical Union, which coordinates global astronomical research, had issued a carefully worded statement encouraging timely sharing of observations related to interstellar visitor 3I Atlas to enable appropriate scientific analysis by the global research community. The statement stopped short of criticizing specific space agencies, but it represented the first official acknowledgement that the delays were becoming problematic for normal scientific processes. Several major astronomical journals had also published editorials discussing the importance of rapid data sharing for objects of such obvious scientific significance. As October 29th approached, observatories around the world were making final preparations for tracking 3I Atlas through its perihelion passage. While the object would be invisible from Earth due to solar glare, space-based solar observatories might be able to detect its presence indirectly through effects on the solar wind or corona. The Solar Dynamics Observatory, the Parker Solar Probe, and ESA's Solar Orbiter all had instruments capable of detecting disruptions in the solar environment that might be caused by a large object passing close to the Sun. If 3I Atlas exhibited any unusual activity during perihelion mass ejections, artificial propulsion, or deployment of smaller objects, these solar monitoring spacecraft might provide indirect evidence. But even these solar observations would require careful analysis and interpretation. Natural comets could produce significant disruptions in the solar environment through outgassing and gravitational effects. Distinguishing between natural and artificial causes would require detailed modeling and comparison with previous cometary perihelion passages. The scientific community was preparing for several possible scenarios. If 3I Atlas behaved like a normal comet during perihelion, it should emerge in late November significantly brighter and more active, with well-developed gas and dust tails. If it fragmented due to thermal stress, multiple components should appear when it became visible again. But if 3I Atlas was something other than a natural comet, its post-perihelion appearance might be dramatically different. It could emerge on a modified trajectory, indicating that propulsive maneuvers had been executed during the hidden passage. It could appear less active than expected, suggesting that its previous outgassing had been artificial rather than driven by solar heating. It could be accompanied by smaller objects that weren't present before perihelion. Most significantly, it could fail to emerge at all, having used the perihelion passage to decelerate and enter a permanent orbit around the Sun, rather than continuing on its hyperbolic trajectory toward interstellar space. 9 days remained until perihelion, 9 days during which the greatest mystery in modern astronomy would either be resolved through official data release, or would disappear behind the Sun with its secrets intact, leaving humanity to wait weeks more for answers that might never come. The silence continued, as carefully orchestrated and as revealing as any statement the space agencies could have made. October 28, 2025, 24 hours remained until 3I Atlas would reach perihelion and disappear behind the Sun, carrying with it the most important unanswered questions in modern astronomy. The object's journey from the outer solar system to its closest approach had been monitored by instruments around the world, but the most crucial observations, those conducted by 7 spacecraft, during the October 3rd Mars flyby, remained locked in secure facilities, accessible only to those with appropriate clearances. The astronomical community had reached a state of barely contained frustration. Dr. Alan Stern, former principal investigator for NASA's New Horizons mission to Pluto, published an open letter that was rapidly circulating through professional networks. For decades of planetary science, I have never witnessed such a deliberate withholding of scientifically significant observations. The October 3rd flyby represented the best opportunity in human history to study an interstellar visitor at close range. The data from that encounter belongs not to any single agency or nation, but to humanity itself. The letter was signed by more than 200 prominent astronomers, planetary scientists, and SETI researchers from institutions around the world. It represented the first coordinated public pressure on space agencies to release the Mars flyby observations, but it produced no immediate response from NASA, ESA, CNSA, or the UAE space program. Meanwhile, final preparations were underway for monitoring 3I Atlas during its perihelion passage. While the object would be invisible to conventional telescopes due to solar glare, several space-based solar observatories were positioned to detect indirect evidence of its presence and behavior. NASA's Solar Dynamics Observatory, despite the government shutdown complications, would continue its automated monitoring of solar activity. Any significant disruption in the solar wind or coronal structure caused by 3I Atlas's passage would be recorded by SDO's instruments, even if analysis of that data would be delayed by staffing limitations. The Parker Solar Probe, humanity's closest approach to the Sun, was particularly well positioned to observe 3I Atlas indirectly. Parker's instruments could detect changes in the solar wind particle flux, magnetic field variations, and other signatures that might indicate the presence of a large object in the inner solar system. ESA's solar orbiter would provide an independent perspective on the perihelion passage, potentially detecting 3I Atlas through its effects on the solar environment from a different vantage point. The combination of multiple solar monitoring spacecraft could potentially reconstruct 3I Atlas's behavior during perihelion even without direct optical observations, but these indirect observations would require weeks or months of analysis to yield meaningful results. The immediate question facing the astronomical community was whether 3I Atlas would emerge from its solar occultation fundamentally unchanged or exhibiting characteristics that couldn't be explained through natural commentary processes. The betting among professional astronomers was running heavily toward natural explanations. Dr. Michael Ahern, one of the world's leading comet experts, had published a detailed analysis arguing that all of 3I Atlas's observed anomalies could be explained through exotic but natural processes. Interstellar comets formed in environments very different from our solar system. Unusual chemical compositions, atypical outgassing patterns, and even statistical coincidences in trajectory are all within the realm of natural possibility. The burden of proof for artificial origin hypotheses remains extraordinarily high, but a significant minority of researchers were becoming convinced that 3I Atlas represented something unprecedented. Dr. Avi Loeb continued to argue that the cumulative evidence, the statistically improbable trajectory, the industrial-grade nickel production, the wow signal correlation, and especially the coordinated silence from multiple space agencies pointed toward artificial origin with increasing confidence. The Copernican principle suggests that we are not special observers in the universe. Loeb wrote in his latest analysis, if we can conceive of launching interstellar probes to investigate nearby star systems, we should expect that more advanced civilizations have already done so. 3I Atlas may represent our first encounter with such a probe, and the reaction of our space agencies suggests they have observed something that challenges conventional astronomical assumptions. The debate had moved beyond academic circles into mainstream media coverage, with major news organizations running detailed analyses of the silence surrounding 3I Atlas observations. Public interest was reaching levels normally reserved for major space missions or significant scientific breakthroughs. Polling data suggested that approximately 60% of the American public believed that space agencies were withholding important information about 3I Atlas, while 40% accepted official explanations about data processing delays and government shutdown complications. International polling showed similar patterns, with majorities in most countries expressing skepticism about the extended silence. The political implications were becoming significant. Congressional hearings about the government shutdown had begun to include questions about its impact on 3I Atlas research. Several senators had demanded briefings about the Mars flyby observations, arguing that taxpayer-funded research should be made available to the public in a timely manner. But these political pressures were limited to the United States. ESA, CNSA, and the UAE space program faced different political structures and accountability mechanisms. Their continued silence couldn't be attributed to American domestic politics, suggesting either that their observations had been unsuccessful or that international coordination was preventing normal data release processes. Amateur radio astronomers had been monitoring frequencies around 1,420 MHz, the hydrogen line frequency associated with the 1977 WOW signal, hoping to detect any artificial transmissions from 3I Atlas as it approached perihelion. Several groups reported possible detections, but none could be verified or replicated by independent observers. The most significant amateur observation came from the Arecibo Successor Telescope in Puerto Rico, which detected what appeared to be structured radio emissions from 3I Atlas's general direction on October 27th. The signal lasted approximately 15 minutes and showed characteristics similar to the WOW signal: narrow bandwidth, specific frequency, and apparent artificial origin. But the detection occurred during daylight hours when 3I Atlas would have been very close to the sun's position in the sky, making confirmation difficult. So the radio interference could easily account for unusual signals from that direction, and professional radio astronomers were skeptical about attributing the detection to 3I Atlas without additional verification. As October 28th progressed toward its end, 3I Atlas was approaching the point where it would become completely invisible from Earth-based telescopes, so the glare was already making detailed observations impossible for all but the most sophisticated instruments, and within hours the object would disappear entirely behind the sun's disk. The final ground-based observations showed 3I Atlas continuing to brighten and develop a more prominent tail as it approached perihelion, behavior consistent with normal cometary activity under intense solar heating. But these observations lacked the resolution needed to detect the subtle structural or chemical anomalies that might distinguish between natural and artificial objects. Space agencies maintained their silence through the final hours. No last-minute data releases, no preliminary statements about the October 3rd observations, no hints about what might be expected during or after the perihelion passage. The coordinated reticence that had characterized the entire post-flyby period continued unchanged as 3I Atlas approached its moment of closest solar approach. At 23:47 Universal Time on October 28th, 3I Atlas made its final appearance in ground-based telescopes before disappearing into solar glare. Amateur astronomers around the world captured what they hoped would be the last images of the interstellar visitor as a free-flying object in space when 3I Atlas emerged from behind the sun in late November or early December. It would either vindicate the natural comet hypothesis or confirm that humanity had encountered something requiring entirely new categories of explanation. But for the next several weeks, the most important astronomical object of the 21st century would be hidden from human observation, free to behave in ways that might fundamentally change our understanding of our place in the universe. The waiting began October 29, 2025, 14:23 Universal Time. 3I. Atlas reached perihelion at a distance of 1.36 astronomical units from the Sun, roughly 203 million kilometers, positioning it between the orbits of Earth and Mars at the moment of its closest solar approach. For the first time since its discovery in July, the interstellar visitor was completely invisible to Earth-based observation, hidden behind the overwhelming glare of our home star. The moment was both anticlimactic and profoundly significant. Anticlimactic because nothing dramatic was visible from Earth 3I. Atlas simply faded into solar glare and disappeared from telescopic view, much as any comet would under similar circumstances. Significant because this marked the beginning of a crucial test period during which the object's true nature might finally be revealed. Through its behavior under extreme solar conditions. If 3I Atlas was a natural comet, perihelion should trigger spectacular activity. The intense solar radiation, approximately 12 gigawatts of power, continuously hitting the object's surface, should drive massive outgassing. As subsurface ices reached sublimation temperatures, complex organic compounds should begin breaking down under the thermal stress. The nucleus might fragment if structural weaknesses existed, potentially splitting into multiple components that would become visible when the object emerged from solar occultation. But if 3I Atlas was something else, if any of the artificial origin hypotheses had validity, perihelion might trigger very different behavior patterns. The orbital mechanics were particularly intriguing. Perihelion represented the optimal point for major trajectory modifications. Through the Oberth effect, any propulsive maneuver executed at closest approach would be amplified by the deep gravitational well, allowing significant orbital changes with minimal energy expenditure. A natural comet on a hyperbolic trajectory would continue past perihelion and head back toward interstellar space, gradually fading as it moved away from the Sun. But an artificial object could potentially execute a reverse Oberth maneuver, decelerating to capture itself into an elliptical solar orbit, rather than continuing on its escape trajectory. Such a maneuver would be completely undetectable from Earth due to the solar occultation. The thermal and radiation environment around perihelion would mask most propulsion signatures, and radio communications with the hidden object would be impossible due to solar interference. If 3I Atlas intended to establish a permanent presence in our solar system, perihelion would provide perfect cover for the transition from interstellar visitor to solar system resident. The possibility of payload deployment was equally troubling. The retrograde orbit that had brought 3I Atlas to perihelion made this the optimal point for releasing smaller probes designed for inner system reconnaissance. Objects deployed at perihelion with minimal velocity could intercept Earth's orbit with relatively little energy expenditure, taking advantage of the opposite orbital motions to achieve efficient transfer trajectories. From an engineering perspective, deploying reconnaissance probes at perihelion would be elegant and efficient. The mothership could continue on its original trajectory, maintaining the appearance of a normal cometary passage, while smaller objects began independent missions to investigate Earth, Venus, or other inner system targets. These deployment scenarios had been analyzed in detail by several research groups, most notably Dr. Loeb's team at Harvard. Their calculations showed that objects as small as a few meters across could reach Earth orbit within 6 to 12 months if deployed from 3I Atlas during its perihelion passage. Such objects would be virtually undetectable during transit too, small to be observed by current space surveillance networks, but large enough to carry sophisticated reconnaissance equipment. They could establish Earth orbital positions months before being detected. If they were detected at all. The space-based solar observatories that were monitoring the perihelion region provided humanity's only real-time insight into what might be occurring during 3I Atlas's hidden passage, but their observations would be indirect, limited to detecting the object's effects on the solar environment rather than observing its behavior directly. NASA's Solar Dynamics Observatory continued its automated operations despite government shutdown complications, recording high-resolution images of the solar corona and monitoring magnetic field variations that might indicate the presence of a large object in the inner solar system. The Parker Solar Probe, positioned closer to the Sun than any human-made object in history, was particularly well situated to detect 3I Atlas indirectly through changes in solar wind particle flux, magnetic field measurements, and other environmental factors. ESA's solar orbiter provided an independent perspective from a different orbital position, potentially capable of triangulating 3I Atlas's location and behavior through coordinated observations with other solar monitoring spacecraft. But these indirect detection methods required careful analysis to distinguish between natural cometary effects and potentially artificial activities. Large comets could produce significant disruptions in the solar environment through normal outgassing and gravitational effects. Determining whether 3I Atlas was behaving unusually would require detailed comparison with previous cometary perihelion passages. The analysis would take weeks or months to complete, meaning that even if artificial activities occurred during perihelion, confirmation might not come until long after 3I Atlas had emerged from solar occultation. Meanwhile, ground-based observatories around the world were preparing for the re-emergence observations that would begin in late November. The Very Large Telescope, the Atacama Large Millimeter Array, and dozens of other major facilities had reserved observation time to capture the first post-perihelion images of 3I Atlas. These observations would be crucial for determining what, if anything, had changed during the hidden passage. A natural comet should emerge significantly brighter and more active, with well-developed gas and dust tails streaming away from the Sun. Any fragmentation that occurred during perihelion should be immediately visible as multiple objects where previously there had been one, but artificial objects might display very different post-perihelion characteristics. They could emerge less active than expected if their previous outgassing had been artificially controlled, rather than driven purely by solar heating. They could appear on modified trajectories if propulsive maneuvers had been executed. During occultation, they could be accompanied by smaller objects that weren't present before perihelion. Most dramatically, they could fail to emerge at all, having used the perihelion passage to establish permanent solar orbits rather than continuing toward interstellar space. The international coordination required for comprehensive re-emergence observations was being complicated by the continuing U.S. government shutdown. NASA's participation in planning meetings was limited by staffing reductions, and critical decisions about spacecraft positioning for optimal observation geometry were being delayed by bureaucratic complications. ESA was attempting to coordinate the international effort, but the absence of full American participation was hampering the development of comprehensive observation strategies. Critical assets like the Hubble Space Telescope and the James Webb Space Telescope required NASA involvement for scheduling and operation. China's space program remained conspicuously silent about their plans for post-perihelion observations. CNSA had the technical capability to contribute significantly to the international effort, but their failure to release any information about their October 3rd Mars observations suggested they might be pursuing independent analysis rather than participating in coordinated international efforts. The silence that had characterized the entire post-Mars flyby period showed no signs of breaking during the perihelion passage. If anything, the coordinated reticence from multiple space agencies had deepened, with even routine administrative communications becoming increasingly guarded. Amateur astronomers were left to conduct their own preparations for re-emergence observations, organizing informal networks to ensure comprehensive sky coverage when 3I Atlas became visible again. Several groups had established rapid response protocols for sharing observations and coordinating follow-up observations if unusual features were detected. The most ambitious amateur effort was being coordinated by the International Amateur Radio Union, which had organized listening posts around the world to monitor for artificial radio transmissions. When 3I Atlas emerged from solar occultation, the effort was partly inspired by the possible WOW signal connection, but also represented a recognition that professional radio astronomy facilities might be focused on conventional observations to detect unusual signal characteristics. As the hours of perihelion passage stretched on, 3.1 Atlas was experiencing the most intense solar radiation of its journey through our solar system. If it was a natural comet, this was the moment when its nucleus would be subjected to maximum thermal stress, when the most violent outgassing would occur, when any structural weaknesses would manifest as catastrophic fragmentation. If it was something else, this was the moment when it might reveal its true nature, through actions that no natural object could survive or execute. But for now, 3.1 Atlas remained hidden behind the solar veil, invisible to human observation, free to behave in ways that might fundamentally challenge our understanding of what was possible in the cosmos. The waiting continued, with answers weeks away and speculation reaching fever pitch. In astronomical communities around the world, November 15, 2025, 17 days had passed since 3I Atlas disappeared behind the Sun, and the astronomical community had settled into an uneasy period of preparation and speculation. While waiting for the object's re-emergence, the coordinated silence from space agencies regarding the October 3rd Mars flyby observations had continued unbroken, even as political and scientific pressure for disclosure mounted worldwide. The timing of the solar occultation couldn't have been more frustrating. Just as humanity had achieved its most detailed observations of an interstellar visitor, the object had vanished from view during its most active phase, leaving crucial questions unanswered about its nature and behavior. The period of invisibility was expected to last another 2 to 3 weeks, during which 3I Atlas would either undergo natural cometary evolution or potentially execute maneuvers that could only be detected after the fact. Congressional pressure on NASA had intensified following the end of the government shutdown on November 3rd, with federal employees returning to work. They were no longer bureaucratic excuses for withholding scientific data that had been collected. More than a month earlier, several House Science Committee members had demanded classified briefings about the Mars flyby observations, arguing that taxpayer-funded research should be made available to both Congress and the public. But the briefings, when they finally occurred, apparently only deepened the mystery. Representative Sarah Martinez, ranking member of the House Subcommittee on Space, Science, and Technology, emerged from a closed-door NASA briefing on November 10th with a carefully neutral statement. The committee has been informed about ongoing analysis of observations related to the interstellar visitor 3I Atlas. We understand that this analysis requires careful scientific review before public release, and we support NASA's commitment to rigorous scientific standards. The statement was notable for what it didn't say. No timeline for public release, no characterization of the observations as routine or unusual, no dismissal of the speculation that had been building in scientific communities. If the Mars flyby data showed nothing more than a typical comet, congressional representatives would have said so directly to reassure constituents and end the mounting speculation. International pressure was also building. The European Space Agency faced pointed questions from member nation representatives about why their October 7th release of basic 3I Atlas images had not been followed by more detailed analysis or spectroscopic results. ESA Director General Dr. Ashbacher had responded with increasingly terse statements about ongoing scientific review and coordination with international partners. China's continued silence was becoming a diplomatic issue. The China National Space Administration's failure to release any observations from Tianwen-1 was being interpreted by some observers as evidence of a breakdown in international scientific cooperation. However, sources within the Chinese space program suggested that the silence was coordinated with other agencies rather than resulting from technical failures or political conflicts. The UAE space program faced similar questions from international partners who had supported the Emirates Mars mission as a collaborative scientific endeavor. The failure to share Hope orbiter observations of such a significant astronomical event was straining relationships that had been carefully cultivated over years of mission development. The solar observatories that were monitoring 3I, Atlas's perihelion, passage indirectly had begun producing preliminary results, but these observations raised more questions than they answered. NASA's Solar Dynamics Observatory had detected several unusual disturbances in the solar corona during the expected time frame of 3I, Atlas's closest approach, but determining whether these were related to the comet's presence or represented normal solar variability required extensive analysis. The Parker Solar Probe had recorded what appeared to be structured variations in solar wind particle flux on October 30th and 31st, but the signals were subtle and could easily be attributed to natural solar phenomena. More troubling were magnetic field measurements that showed periodic variations with a 4-7-hour cycle to regular to be easily explained by random solar activity, but too brief to match 3I, Atlas's estimated 7.3-hour rotation period. ESA's solar orbiter had detected complementary anomalies from its different vantage point, suggesting that the source of the disturbances was indeed located in the inner solar system, rather than being artifacts of individual instrument systems. But the data was complex and would require months of analysis to yield definitive conclusions about what might have caused the observations. The amateur astronomy community had become increasingly organized during the waiting period, establishing observation networks and communication protocols for the anticipated re-emergence of 3I, Atlas. Several groups had developed sophisticated image processing techniques for extracting maximum information from relatively modest telescope systems. Dr. Robert Warwick, the astronomer who had originally discovered Oumuamua in 2017, had been coordinating an international network of amateur observers in preparation for 3I, Atlas's reappearance. His experience with the challenges of observing fast-moving interstellar objects made him uniquely qualified to organize effective observation strategies. The professional observatories will obviously provide the highest quality data, Warwick explained in a widely circulated email to participating amateur astronomers, but they also have limited observation time and predetermined research priorities. Amateur networks can provide continuous monitoring and rapid response to unexpected developments that might be missed by scheduled professional observations. The amateur effort had been complicated by the continuing secrecy surrounding the October 3rd professional observations. Without knowing what anomalies might have been detected during the Mars flyby, amateur observers were uncertain about what features to look for during re-emergence observations. Some groups were focusing on conventional cometary characteristics, brightness, tail development, and fragmentation signatures that would indicate normal post-perihelion behavior. Others were specifically looking for anomalies that might support artificial origin hypotheses, unusual structural features, non-cometary trajectories, or accompanying objects that weren't present before perihelion. The most ambitious amateur project was being coordinated by the International Amateur Radio Union, which had established a global network of listening posts to monitor for artificial radio transmissions when 3I, Atlas became visible again. The effort was inspired partly by the possible WOW signal connection, but also by the recognition that artificial objects might attempt to communicate or conduct reconnaissance activities during their closest approach to Earth. Professional SETI organizations had been notably quiet about 3I, Atlas, possibly due to funding constraints or skepticism about the artificial origin hypotheses, but several prominent SETI researchers had privately expressed interest in the radio monitoring efforts, suggesting that the scientific establishment was taking the possibility more seriously than public statements indicated. Dr. Jill Tarter, former director of SETI research at the SETI Institute, had published a carefully worded editorial discussing the importance of keeping open minds about unusual astronomical observations. The history of astronomy is filled with discoveries that initially seemed to violate natural laws, but eventually led to expanded understanding of cosmic processes. whether 3i Atlas represents exotic natural phenomena or something more extraordinary. It deserves careful scientific investigation free from preconceived assumptions about what is possible in the universe. The editorial was interpreted by many observers as implicit support for taking the artificial origin hypotheses seriously, even though Tata stopped short of endorsing any specific interpretation of the available evidence. Betting markets had begun offering odds on various 3i Atlas scenarios, with natural comet explanations favored at approximately 3-to-1 odds over artificial origin hypotheses. More specific bets were available on whether the object would emerge on its original trajectory, whether it would show evidence of fragmentation, and whether any accompanying objects would be detected. The markets reflected the deep uncertainty that characterized professional astronomical opinion. While most scientists publicly maintained that natural explanations were most likely, private conversations revealed significant doubt about whether conventional cometary physics could account for all of 3i Atlas's observed characteristics. The combination of the statistically improbable trajectory, the industrial-grade nickel production, the wow signal correlation, and especially the coordinated silence from multiple space agencies had created a level of scientific uncertainty that was almost unprecedented in modern astronomy. Even conservative researchers were beginning to acknowledge that 3i Atlas might represent phenomena beyond current theoretical understanding. As November progressed toward the anticipated re-emergence date, tension was building throughout the international astronomical community. Observatory schedules were being adjusted to ensure maximum coverage of the sky region, where 3i Atlas was expected to appear. Emergency observation protocols were being established in case the object exhibited unexpected behavior that required immediate follow-up. The stakes couldn't have been higher. If 3i Atlas emerged as a normal comet, continuing on its original trajectory with typical post-Perihelion characteristics, it would vindicate natural explanation and resolve one of the most controversial astronomical discoveries in recent history. But if it emerged exhibiting artificial characteristics modified trajectory, unusual structural features accompanying objects, or behavioral patterns inconsistent with natural cometary processes, it would represent the most significant discovery in human history, definitive evidence that we are not alone in the universe, and that other intelligences are actively investigating our solar system. The answer was less than 3 weeks away, hidden somewhere in the solar glare, approaching the moment when it would either confirm our understanding of cosmic processes or fundamentally challenge our assumptions about our place in the universe. As December 2025 approaches and the astronomical community prepares for 3i Atlas's re-emergence from behind the Sun, the questions surrounding this extraordinary interstellar visitor remain as compelling as ever. More than 2 months have passed since 7 spacecraft achieved humanity's closest observations of an object from another star system, yet the data from those encounters remains locked away, accessible only to those with the highest security clearances. The silence itself has become the most significant piece of evidence in a puzzle that challenges our fundamental assumptions about what is possible in the cosmos. For independent space agencies, operating under different political systems and scientific protocols, have maintained coordinated reticence about observations that should have been routine scientific achievements, worthy of immediate publication and international celebration. This coordination suggests something far more significant than bureaucratic delays or technical complications. It implies a discovery so extraordinary that it requires consultation at the highest levels of government before public release, a discovery that might fundamentally change humanity's understanding of its place in the universe. The circumstantial evidence continues to accumulate, a trajectory with less than 1 chance in 200,000 of occurring randomly. Industrial-grade nickel production that matches human metallurgical processes better than any known natural phenomenon. Possible connections to the most famous unsolved mystery in SETI research, and behavioral characteristics that strain conventional explanations for cometary activity. Individually, Each anomaly might be explained through exotic but natural processes. Collectively, they form a pattern that increasingly resembles what we might expect from advanced technology rather than random cosmic debris. But the most troubling aspect of the entire 3I Atlas affair may be the realization that humanity's first encounter with potentially artificial extraterrestrial objects might occur not through deliberate communication or dramatic revelation, but through gradual recognition that visitors from other star systems have been quietly observing us for decades or centuries. If 3I Atlas represents technology rather than nature, it suggests a level of discretion and subtlety that challenges science fiction scenarios of dramatic first contact. Instead of obvious artificial constructs announcing their presence, we may be dealing with reconnaissance systems designed to blend in with natural phenomena while conducting systematic surveys of emerging technological civilizations. The implications extend far beyond astronomy. If other intelligences are actively investigating our solar system, they presumably have access to information about Earth's biosphere, technological development, and social organization that far exceeds anything we know about their origins or intentions. Are we being evaluated, catalogued, prepared for some form of contact or intervention? Or are we simply one stop on a vast galactic survey that has been ongoing for millions of years, mapping the distribution and development of life throughout the Milky Way? These questions may seem premature given that natural explanations for 3I Atlas's characteristics remain possible, but the extended silence from space agencies suggests that the October 3rd observations revealed something that cannot be easily dismissed or explained through conventional scientific frameworks. When 3I Atlas finally reappears from behind the Sun in the coming weeks, its post-Perihelion characteristics will provide crucial evidence for resolving the central questions about its nature. A natural comet should emerge brighter and more active, with well-developed tails and possible fragmentation signatures. An artificial object might display very different behaviors, modified trajectory, unusual structural features, or accompanying objects that weren't present before perihelion. But even if 3I Atlas proves to be a natural comet with exotic but explainable characteristics, the questions it has raised about our cosmic environment will persist. The statistical analysis of its trajectory will remain valid. The industrial chemistry signatures will require explanation. The coordinated silence from space agencies will need justification. Most importantly, 3I Atlas has demonstrated how unprepared humanity is for ambiguous encounters with potentially artificial objects. Our scientific institutions, governmental structures, and public communication systems are designed to handle clear-cut discoveries that fit established categories of understanding. They are less well-equipped for situations that fall into the uncomfortable middle ground between natural phenomena and obvious artificiality. If 3I Atlas represents our first tentative contact with extraterrestrial intelligence, it has revealed significant gaps in our ability to recognize, analyze, and respond to such encounters appropriately. The months of speculation and secrecy surrounding its observations suggest that we need better protocols for handling discoveries that might challenge fundamental assumptions about our cosmic solitude. The story of 3I Atlas is far from over. When it emerges from solar occultation, new observations will either resolve the current uncertainties or deepen them further. If it proves to be artificial, humanity will face the challenge of determining how to respond to the knowledge that we are being observed by intelligences with technological capabilities far exceeding our own. If it proves to be natural but anomalous, we will need to expand our understanding of cosmic processes to account for phenomena that currently challenge our theoretical frameworks. Either way, 3I Atlas has already succeeded in forcing humanity to confront questions we may not be ready to answer. Are we alone in the universe? If not, are we being watched? And if we are being watched, what does that mean for our future as a species reaching tentatively beyond our home world, into the vast cosmic ocean that surrounds us? The answers to these questions may determine not just our understanding of the universe, but our place within it. They lie waiting somewhere in the classified archives of the world's space agencies, in the hidden behavior of an object approaching its moment of truth behind the sun, and in observations yet to be made when 3i, Atlas finally reveals whether it represents the most unusual natural visitor our solar system has ever received, or something far more extraordinary. The October silence may be ending, but the questions it has raised will echo through human consciousness. Long after 3i, Atlas disappears back into the interstellar void from which it came, we are no longer certain that we observe the cosmos in solitude, and that uncertainty may be the most important discovery of all.